JCE Advanced Level Chemistry Practical Series Experiment number 20. Determination of the concentration of potassium permanganate solution using standard acidified potassium oxalate solution. So in this experiment, students, we are going to be preparing a standard solution of potassium oxalate, and using that we are going to titrate a potassium permanganate solution so that we can find out the concentration of a potassium permanganate solution. So the aim of this experiment is to provide the necessary knowledge to prepare a known concentration of a primary standard solution. So when you are carrying out a titration like this, you should be able to prepare a primary standard solution. So in order to do that, you need to carry out calculations to find out the number of moles of the primary standard that you should have in your solution. And then you need to measure the mass of the necessary amount of primary standard. And then you need to prepare the solution. So we are going to learn how to make a primary standard solution here. We have actually learned the preparation of a primary standard in the previous experiments as well. Here also we'll be very briefly looking into that. And the next mentioned aim of this experiment is to determine the concentration of permanganate ion solution using a redox titration. So students, the primary standard solution we are using for this experiment is oxalate ions or potassium oxalate. So potassium oxalate contains oxalate ions, and oxalate ions and permanganate ions undergo a redox reaction. Permanganate ions in acidic medium will get reduced to Mn2+, while oxalate ions will get oxidized to carbon dioxide. So what you see over here when we are carrying out this titration is a redox reaction. So this is also known as a redox titration that can be carried out to determine the concentration of potassium permanganate solution that we have. So when you are finding out the concentration of a solution like potassium permanganate with the use of a primary standard solution, students, after finding out the concentration of potassium permanganate solution, it becomes what is known as a secondary standard. So now let's move on to the next slide. What is meant by a primary standard? A compound labeled as a primary standard has an absolute known concentration or composition, and can be obtained in high purity, and it can be stored as a solid or a solution without undergoing any change. So students, a primary standard is a substance that we know the composition of very accurately and that can be stored without it having undergone any changes while we store it. So, and we should know the purity of the substance as well, and usually primary standard substances have high purity. If the purity levels are low, at that point will not qualify to be a primary standard. Qualities primary standard should have: it should have high purity, high stability. They should be stable if they undergo change when they are stored. Again, then we can't be sure of their composition. So when we are not sure of their composition, for example, if you are trying to measure a certain mass of the primary standard substance and you expect a certain number of moles of that substance to be there in that mass. If the composition is not what you think it is, at that point the number of moles of the primary standard in the mass of the primary standard that you measure might not be what you want it to be. For example, students, if you measure 5 grams of, let's say, potassium oxalate, and you expect a certain number of moles of potassium oxalate to be in that 5 grams. But imagine, due to certain reasons, the composition of potassium oxalate has changed and the oxalate ion percentage in the solid has gone down. So at that point, the number of moles of potassium oxalate in the 5 grams of potassium oxalate you measured might have gotten lowered. So although you assume that there are a certain number of oxalate anions or potassium oxalate in 5 grams of potassium oxalate, you might not introduce that expected number of moles into your solution. Should be anhydrous. It should not contain any water in it. Should have very low hygroscopy. If the substance absorbs water from the surrounding, especially when you're trying to measure a standard solution, when it absorbs water from the surrounding, this will introduce an error into your mass readings. So it should not be hygroscopic. Should be non-toxic, should be inexpensive, should be easily available, it shouldn't be scarce, should have a high molecular mass. Now, high molecular mass is important when we are trying to avoid or when we are trying to minimize the measurement errors, mass measurement errors. So when you're measuring a larger mass, the percentage error in a larger mass is going to be small. But when you're measuring an extremely small amount of mass with the same balance, you would notice if the balance has a specific amount of error, then the error percentage in the small mass measurements are going to be higher. In large mass measurements, it's going to be a smaller percentage error. So if the molecular mass or molar mass of the substance is higher, at that point, students, it will be more suitable to be used as a primary standard. Should be easy to weigh, and should be very low in reactivity. Now, again, it should be very easy to weigh. For example, if you are trying to measure the mass of certain amount of sodium hydroxide, you would notice as you measure the mass of sodium hydroxide, when you try to scoop up a small mass of sodium hydroxide pellets from the sodium hydroxide container, the pellets look dry. However, once you transfer them into the watch glass, as you carry out the mass measurement for a period of, let's say, like 30 seconds, you will notice that the sodium hydroxide pellets are no longer dry. They appear wet. There will be a certain amount of water that is absorbed onto our sodium hydroxide pellets because sodium hydroxide is hygroscopic. It will absorb water from the surrounding. So students, because of this reason, sodium hydroxide is not easy to weigh. So whatever your primary standard substance should be easy to weigh, and they should not be very reactive as well. Now again, if you take sodium hydroxide as an example, as we weigh sodium hydroxide, certain amount of sodium hydroxide can react with carbon dioxide in the atmosphere and it can turn into sodium carbonate. So students, again, another thing that you need to keep in mind is your primary standard should be low in reactivity. Compounds used as primary standards. So these are some of the compounds that are going to be used as primary standards: potassium oxalate, sodium oxalate, and oxalic acid. So for today's experiment, you can use either one of these because each of these contains an oxalate anion. So apart from potassium oxalate, sodium oxalate, and oxalic acid, we have other primary standards here: sodium carbonate, potassium dichromate, potassium bromate, potassium iodate, and even potassium hydrogen iodate can be used. Arsenic trioxide, sodium tetraborate, potassium hydrogen phthalate. The formula of potassium hydrogen phthalate is given here. Potassium hydrogen phthalate, this is the structure of potassium hydrogen phthalate, and there are two different forms of the formula of potassium hydrogen phthalate given here. So when you take a look at these formulas, you should be able to understand that what we are talking about is potassium hydrogen phthalate, a primary standard. Now we are looking into why certain substances. In this slide, we are going to look at why certain substances like sodium hydroxide and HCl can't be used as a primary standard. Why sodium hydroxide is not a primary standard. Difficulties in accurately weighing due to the absorption of water causing dissolution of sodium hydroxide crystals. So students, due to hygroscopic nature of sodium hydroxide, when you are trying to weigh sodium hydroxide, certain amount of water vapor will get adhered to these sodium hydroxide pellets and will dissolve certain amount of sodium hydroxide in them. And due to water vapor getting mixed with sodium hydroxide, the mass of just the sodium hydroxide cannot be accurately weighed because certain amount of water vapor is now in the sodium hydroxide. Apart from that, carbon dioxide can react with sodium hydroxide to form sodium carbonate. So we know that this is happening while we measure the mass of sodium hydroxide. So the composition of sodium hydroxide that you are measuring is not very accurate because we know certain amount of sodium hydroxide is now reacting with carbon dioxide to form sodium carbonate. Challenges in stable long-term storage of sodium hydroxide. So this means you can't store sodium hydroxide without the composition of sodium hydroxide changing over a longer period of time. So these are the reasons why we can't use sodium hydroxide as a primary standard. Now let's take a look at HCl. HCl is also not a primary standard. HCl is a gas at room temperature. HCl is a gas at room temperature. So you might have experienced this when you are conducting experiments. When HCl is produced as a product, you might have noticed that white color fumes or white fumes are produced. And this is a observation that you associate with the formation of HCl gas. HCl gas, when it is produced in a reaction, it appears to be a white color fume, sometimes known as misty fumes as well. So this white fume indicates the formation of HCl, and HCl is a gas at room temperature. Actually, when you are opening a stock bottle of HCl, you actually see the fumes of HCl, right? If you take a wet blue litmus paper, it will turn red if you hold a wet blue litmus paper over a stock bottle that is open of HCl. If you open a stock bottle of HCl and bring a wet litmus paper, a blue litmus paper will turn red. This indicates that the gas that was involved here is acidic. So it is none other than HCl vapor or HCl gas. So HCl is a gas at room temperature. It is difficult to properly weigh HCl or measure the volume of HCl because even when you are measuring the volume of HCl, a certain amount of HCl can undergo evaporation in room temperature. So HCl can evaporate easily in room temperature, not in very dilute solutions. However, in concentrated HCl solutions, you will observe HCl can easily undergo evaporation. HCl cannot be stored without changes to its composition at room temperature. So when you are storing it at room temperature for longer periods of time, it can undergo changes to its composition. So because of these reasons, we can't consider HCl to be a primary standard. Now in this slide, we are going to look at why potassium permanganate and ferrous sulfate is not considered to be primary standards. So first reason is obtaining high purity is challenging due to the presence of manganese dioxide in potassium permanganate. So when you take potassium permanganate, it is not going to be having a really high purity because certain amount of potassium permanganate solid is going to contain a little bit of manganese dioxide, MnO2. So it is very difficult to obtain potassium permanganate without the presence of MnO2 or manganese dioxide impurities. Potassium permanganate, being an oxidizing agent, alters its composition when reacting with organic matter in air. In air, you have certain organic matter that can come into contact with our potassium permanganate solutions. So potassium permanganate is a good oxidizing agent. So when it comes into contact with organic matter in air, this organic matter can be oxidized with the help of potassium permanganate. So as potassium permanganate oxidizes this organic matter, potassium permanganate itself undergoes a reduction. So because of this, the composition of potassium permanganate solutions you have prepared will change over time. If you prepare potassium permanganate solution today, after a couple of days, you will observe the color of the potassium permanganate solution has slightly changed, actually reduced. This is because certain amount of potassium permanganate has reacted with other substances in air. Potassium permanganate reduces to Mn2 plus in acidic medium and to MnO2 in neutral and alkaline medium. So if the solution that you have prepared is neutral or alkaline, it will reduce to MnO2. So apart from color of the solution reducing, you will sometimes find brown color, black brown color, MnO2 solid particles as well. And if it is present in acidic medium, potassium permanganate will reduce to Mn2 plus. And potassium permanganate can undergo decomposition in sunlight as well as under heat. So potassium permanganate can undergo decomposition in sunlight or under heat. So this is also not a good quality that is seen in a primary standard. So primary standards will not have qualities like this. So therefore, potassium permanganate is not a primary standard. Reasons why ferrous sulfate is not a primary standard. Let's take a look at those. Now, ferrous sulfate compound crystals exist in hydrated form. Majority of the time, when you try to obtain ferrous sulfate solid is going to contain water of crystallization, meaning it is going to be present in the hydrated form. So, when you are talking about primary standards should be anhydrous. They should not have any water of crystallization. Aqueous Fe2 plus ions undergo oxidation to Fe3 plus in the presence of oxidants in air. Actually, students, Fe2 plus can easily undergo oxidation in air to form Fe3 plus. One good example would be if you prepare a Fe2 plus ion solution, the initial color of the solution is going to be a pale green color. But as you allow it to stand in air for a while, you will observe this pale green color gradually changes. It gradually changes to a yellow-brown color. So this is an indication that more and more Fe3 plus is formed. So the pale blue color goes down and more of a brown color, yellow-brown color will be formed. So as Fe3 plus concentration increases, this color change takes place. So this happens due to oxidation with air. Fe3 plus is formed by Fe2 plus undergoing oxidation. And ferrous sulfate is not a very stable compound. Ferrous sulfate is not a very stable compound, so we can't use ferrous sulfate as a primary standard. Examples for secondary standard solutions. Now, little while ago, we said solutions like HCl, sodium hydroxide, potassium permanganate, they can't be used as primary standards. But we can use them as secondary standards. Some secondary standard examples are given here. Hydrochloric acid, sulfuric acid, sodium hydroxide, potassium hydroxide, and potassium permanganate. Now, they are not going to be primary standards. However, we can standardize solutions of these compounds with the use of a primary standard and then accurately find their concentrations. And when we know the concentration of a solution accurately, we can call it a standard solution. However, this is not a primary standard solution. They are not going to be primary standards because we found out their concentrations by carrying out a titration with a primary standard solution. So these are going to be known as secondary standard solutions. So when it comes to secondary standard solutions, we find their concentration by carrying out a titration with primary standards. Secondary standards refer to substances with higher reactivity that are calibrated using primary standards. So whenever we have a secondary standard solution, majority of the time we can't initially be very sure of its concentration. That means we don't know its concentration accurately. So then what do? We titrate it with a primary standard solution. We carry out our calculations and then we find out the exact concentration of the second or of the solution that we didn't know the concentration of. After we find out its concentration, it becomes a secondary standard solution. So we usually find the concentration of a secondary standard solution before we use it for another titration. We can't store these solutions for a longer period of time. That means if you find the concentration of, let's say, potassium permanganate solution right now today, you can't be sure that concentration is going to be there tomorrow as well. If you want to use the same solution tomorrow or maybe day after, then you will have to carry out another titration with a primary standard to find its concentration. So before we use this type of solutions, we can carry out a titration with a primary standard and find their concentration accurately. And after finding the concentration accurately, we can use them as secondary standards. Primary standards boast higher purity. So when it comes to primary standards, they have higher purity and lower reactivity. Primary standards have higher purity. That's the quality of primary standards. And they have lower reactivity. They can't have really high reactivity because then at that point they will not be very stable. However, secondary standards on the other hand have lower purity and higher reactivity. Now in certain cases, students, for certain reactions, when you're trying to carry out titrations with certain other reactants, you might need a titrant with a high reactivity. But we don't have any primary standards with high reactivity. Then what do? We use a solution or another compound with high reactivity. We can titrate it with a primary standard and find out its concentration. And after converting, let's say, potassium permanganate or whatever the compound with a higher reactivity into a secondary standard solution, we can then use that solution for another titration. So students, this is the reason why we have secondary standards. Especially secondary standards have properties that are slightly different to primary standards, which is a good thing, because if we didn't have secondary standards when it comes to certain chemical reactions where you need to have a very reactive chemical substance titrated against another substance, you will not be able to do a titration like that without the presence of secondary standards. Now, we look into how to prepare a standard solution. How we can prepare a standard solution. First, the mass of a primary standard required to prepare a known volume of standard solution is found by calculation. So very important. We need to measure the mass of a primary standard required to prepare a known volume of the standard solution by calculation. So when you're preparing a primary standard solution, students, you would know the concentration of the standard solution you need to prepare. You would know the volume of the standard solution you need to prepare. So if you know the concentration and the volume, you would know the number of moles of that particular substance present in that volume of your standard solution. So concentration and volume is known, you can find the number of moles. And if you know the number of moles as well as the molar mass of that substance, you can calculate the mass that is needed to prepare your primary standard solution. So first of all, that calculation needs to be done, and then carefully weigh the mass of the primary standard using digital balance, or we can use an analytical balance or triple beam balance. Add the solid crystals into a volumetric flask. So when you're preparing primary standards, you shouldn't be using beakers. You have to use volumetric glassware. Especially when you're preparing a primary standard, it is essential to use a volumetric flask. Dissolve the crystals completely in water. So after transferring the crystals or solid into the volumetric flask, you need to make sure all of the solid crystals are dissolved in water. After we have dissolved all of the solid in water inside the volumetric flask, then you are going to prepare the required volume of solution by adding distilled water all the way up to the calibration mark in the volumetric flask. Now, volumetric flask will have a calibration mark. So after dissolving all the solid, then only you'll be adding distilled water all the way up to the calibration mark, and the bottom end of the meniscus of the solution should align perfectly with the calibration mark on the volumetric flask. So that is how we usually prepare a standard solution. And we now look into different oxidation states of manganese. Different oxidation states of manganese is given here. Presence of +2 to +7 oxidation states of manganese is something special that is seen in manganese-related compounds and ions. It has oxidation states ranging from +2 all the way to +7, you can see here. So +2 oxidation state is observed in +2 ions and manganese chloride. +3 is MnF3 and Mn2O3. And even I think in the previous experiment number 19, we spoke about how Mn2O3 can be formed when we are heating manganese dioxide. And then we have +4 MnO2, +5 MnF5, and +6 MnO4 2-, or we have potassium manganate. So potassium manganate is a green color substance. Don't confuse it with potassium permanganate. Potassium manganate is quite stable in highly alkaline mediums. So that is going to be a green color substance. Potassium permanganate, on the other hand, is a purple color substance. It's in purple color solution when you dissolve it in water. And potassium manganate in alkaline medium, it is going to be stable, and potassium manganate solutions are going to be green color, and potassium permanganate solutions are going to be purple color. And the oxidation numbers are different, +6 and +7 here. You need to remember these oxidation states. Among the above oxidation states, +2, +4 and +7, +2, +4 and +7 are going to be the most common oxidation states of manganese. Now, stable oxidation states of manganese in acidic medium is +2. So, in acidic medium, +2 is going to be your stable oxidation state. That's why we see when we are carrying out reactions with the use of acidified potassium permanganate, as potassium permanganate oxidizes something else, we see permanganate ions turn into Mn2+. Why? Because in acidic medium, Mn2+ is going to be the most stable oxidation state for manganese. And stable oxidation state is +4 in neutral and alkaline medium. And that is again why when we conduct oxidation reactions using permanganate ions in alkaline medium, the reactions stop when a manganese oxidation state has reached +4 oxidation state. So +4 oxidation state is seen in MnO2. So it is going to be produced as a solid, brown color solid. So MnO2 or manganese dioxide is going to be seen in alkaline or neutral solutions when permanganate ions undergo reduction. Permanganate ions oxidize something else, and it by itself, it undergoes reduction, and permanganate ions will undergo reduction to become manganese dioxide in alkaline or neutral medium. So these are the reactions that take place in acidic medium and alkaline medium. I am quite certain, students, by now you know how to write these reactions, and when we are doing some questions we will be writing them from scratch one more time, but I want you to be able to write this type of half equations on your own, right? We have permanganate ions over here turning into Mn2 plus. You need to know in acidic medium that happens, and then oxygens are not balanced, so we add 4 oxygens to this side. At that point, hydrogens will not be balanced on the left hand side. Then we add 8 H pluses here, and when you do that, charges will not be balanced on both sides. So to balance the charges, you will add 5 electrons to the left hand side. And the color change is going to be from purple to light pink or colorless. Now, why do we say light pink or colorless? When it comes to Mn2 plus aqueous ions, Mn2 plus in aqueous medium is going to be pale pink in color, but the color intensity of this complex is extremely low. So therefore, students, you will not observe Mn2 plus aqueous solutions as pink color solutions most of the time. If the Mn2 plus ion concentration is extremely high or relatively high, at that point you will observe the solution turning to a pink or pale pink color. But majority of the time, moderate to low concentrations of Mn2 plus usually appear colorless because the color intensity of this pink color is very low. So majority of the time when you're conducting experiments in the lab, when potassium permanganate, which is a very strong purple color, when potassium permanganate ions turn into Mn2 plus, this very strong purple color appears to be turning colorless. But in fact, what is happening is aqueous Mn2 plus ions are formed. Aqueous Mn2 plus ions are going to be like pink in color, but this light pink color is not very visible to the eye. We have neutral or alkaline medium based reactions. You can see here permanganate ions reduced to form MnO2, which is going to be a brown color solid. So color change is going to be from purple to brown color solid. And when you are balancing equations like this, you can observe on over here MnO4 1 minus has turned into MnO2. We can employ the oxidation number method if you prefer here. Oxidation number method. So permanganate ions have +7 oxidation state here. Manganese dioxide has +4. So this is a reduction. That means since oxidation number has gone from +7 to +4, that is indicative of addition of 3 electrons to the left hand side. So at that point, the overall negative charge on the left hand side is going to be 4. To balance the negative charge in alkaline medium, if you want to add negative charge, now if you have already added electrons to one side, the other side can be added with hydroxide ions because we are talking about alkaline medium. We have enough and more hydroxide. So over here, overall charge 1 minus and 3 minus altogether is going to be 4 minuses. So to balance the charge, you can add 4 hydroxide ions. And at that point, you are introducing 4 hydrogens onto the right hand side. Onto the left hand side, we didn't have any hydrogens. To balance off the hydrogens, we can add 2 water molecules. We have done that here. And when you do that, you can see number of oxygens will also be automatically balanced. Right, students. So now that is just a reminder of how these type of equations can easily be balanced. Either when it comes to acidic medium, we were talking about adding H pluses and water. A similar method can be employed here as well. But again, we discussed a different method here with the use of oxidation numbers. Finding the concentration of aqueous solution of permanganate ions using oxalic acid as a primary standard. We know potassium oxalate or oxalic acid or sodium oxalate can be used to find the concentration of potassium permanganate solution. So in this case, we are going to look how we can use oxalic acid as a primary standard. We'll use a different color. As permanganate is not a primary standard, titration with a primary standard like oxalic acid is crucial to determine its exact concentration. Potassium permanganate is a potent oxidizer exhibiting a dark purple color with KMnO4 minus ions and a light pink color or colorless hue when reduced to Mn2 plus ions. We know these two color changes, we looked at it earlier. This distinct color change serves as a reliable indicator for determining the titration endpoint. The reactions related to the titration are given here. So at the endpoint, what happens, students, if you are carrying out this titration? At the endpoint, actually, when you are carrying out this titration, potassium permanganate is going to be on the burette. And in the titration flask, we will have our oxalic acid. So oxalic acid is colorless. As it reacts with potassium permanganate, each added potassium permanganate drop will react with the oxalic acid and will turn into a colorless solution again. However, at the end point, what is going to be observed is this colorless oxalic acid solution is going to turn pink. Now, you may ask, you just a little while ago told that Mn2 plus ions have a pink color that is not very visible to the eye. So then what is this pink color you're talking about? The pink color I'm talking about right now is not going to be observed due to Mn2 plus ions being present in the medium. After all of the oxalic acid in the titration flask is completely reacted, then when we add another drop of potassium permanganate, now potassium permanganate drop or potassium permanganate solution has a very dark purple color. However, when just a drop of it is added to now the completely reacted oxalic acid solution, this drop contains enough potassium permanganate to react with whatever the remaining amount of oxalic acid in the medium. However, majority of the potassium permanganate that is present in the drop is not going to react with anything because majority of the oxalic acid is now already reacted. Nothing else is there in the medium. So potassium permanganate is going to retain its purple color. However, just a single drop is added to about 40 milliliters of water. A single potassium permanganate drop is additionally added to just 40 milliliters or more of water. So it is going to be a huge dilution. So this dark purple color, when it is diluted in a drop of dark purple color solution, when it is diluted in 40 milliliters of water, it will appear pink, right? So that is going to be our endpoint. A clear solution turning pink due to the addition of just one extra potassium permanganate drop. So the reaction that is taking place is given here, students. You can see potassium permanganate, this is going to be the reducing reaction. So reduction reaction, you can see it is taking 5 electrons and turning into Mn2 plus. You all should know it by heart by now to write this equation, right? It is not going to be that difficult at the exam if you already know how this equation is written. And then we have oxalate and iron. Oxalate and iron turns into carbon dioxide. The number of atoms on both sides are the same, but the charges are different. So you add 2 electrons onto the right hand side. So that is going to be our oxidation reaction. It's going to be the oxidation reaction, and permanganate reaction is going to be our reducing or reduction reaction. Now then permanganate ion reaction and oxalate ion reaction can be added together as long as the number of electrons involved in both of the reactions are the same. Over here there is the involvement of 5 electrons, over here only 2. So we need to make these 2 electron numbers equal. In order to do that, we need to multiply reaction number 1 by 2 and reaction number 2 by 5. Exactly what we have done here. We have multiplied reaction number 1 by 2 and reaction number 2 by 5. And we have added them together. And when you do that, you get to this final reaction. So you should be able to write a final ionic equation like this without any issue. And we can observe the reaction ratio as well. KMnO4 minus to oxalate anion ratio C2O4 2 minus is 2:5. With every 2 permanganate ions, 5 oxalate anions will react. And then we have the redox reaction again explained a little bit in detail. So students, this is the main reaction that is taking place, and the product is going to be Mn2 plus, a light pink color product. You can't observe its color. This reaction proceeds slowly at room temperature. Very important. Unlike most other titrations that you carry out, this titration or this reaction is a bit slow at room temperature. It won't happen that fast at room temperature. If you try to conduct it at room temperature, you can see whenever you're adding a drop of potassium permanganate, it will retain its color for a longer period of time, right? So you don't know whether you have obtained the endpoint or not for a longer period of time. So at room temperature, this reaction is going to be quite slow. To enhance the reaction rate, heating to approximately around 60 degrees Celsius is necessary. So we can use a heating equipment. Over here we can use something known as a hot plate, or you can use a Bunsen burner and directly provide it with heat, but you need to maintain the heat in the solution somewhere around 60 degrees Celsius. And you can carry out the titration like this. So when you're carrying out the titration, the end point is going to be from clear solution to a pink color solution. We will have potassium permanganate in the burette, and in the titration flask we will have oxalic acid added with 15 cubic centimeters of sulfuric acid, because potassium permanganate will react only in acidic medium. So when this reaction is taking place, when this oxidation of oxalate anion take place, and then finally when all of the oxalate anion in the medium is over, the additional drop of potassium permanganate that comes into the medium will turn the medium from clear to light pink, from clear to a pink color. And while you carry out this reaction, you need to keep heating the titration flask, or else you can, if you don't have a hot plate like this, you can actually use a heating setup where you have a tripod and a Bunsen burner. You can take the titration flask on and off from the heating setup and maintain a temperature of around 60 degrees Celsius. Dilute sulfuric acid is first added to oxalic acid solution in the titration flask, and then potassium permanganate is filled in the burette, and the KMnO4 is added drop wise to the titration flask while shaking or while swirling the titration flask. And as we add potassium permanganate into the titration flask, you will see the potassium permanganate color will disappear. Drop wise, when we add, each drop will carry a little bit of purple color along with it, and when you add this purple color drop into this clear solution, the clear solution will slightly turn purple, but after a while the purple color will disappear because permanganate ions will react with the oxalate ions in the medium. The loss of purple color in the titration flask occurs as the permanganate ions undergo reduction to form Mn2 plus ions. Simultaneously, oxalate ions in the solution will get converted into carbon dioxide. This is what contributes to the observed color change. So like I mentioned, purple color of the drop disappears as it turns into Mn2 plus, and this happens because it reacts with oxalate ions in the medium. Oxalate ions turn into carbon dioxide. So in the medium we have oxalate ions, permanganate drops come in, permanganate drops react with oxalate ions, and permanganate turns into Mn2 plus, oxalate ion turns into carbon dioxide. After all the oxalate ions in the medium have converted to carbon dioxide, the next drop of potassium permanganate added to the medium will remain unreacted. So it will remain unreacted in the titration flask. As the unreacted permanganate ion solution gets diluted, a pink color becomes very clear, signaling the end point of the titration. So students, as I mentioned a few more times earlier, the color change is due to the potassium permanganate drop getting diluted immensely in 40 or 50 milliliters of water. So the last drop of potassium permanganate that comes into the medium doesn't have any oxalic acid or oxalate anions to react with it. So then it stays unreacted. So the last drop of potassium permanganate that comes into the medium gets diluted in that huge volume of solution. So then the color is going to change. Potassium permanganate's dark purple color, when it is quite diluted, will appear pink. Therefore, the solution in the titration flask that is colorless in the beginning of the titration turns to a pink color at the end point. So the color change at the end point is colorless to pink. Color change at the end point is colorless to pink. So we move on to the steps when we are carrying out this particular experiment. We will take 0.05 moles per decimeters cube oxalic acid solution that is going to serve as our primary standard in this titration procedure. 3 samples, each of 25 cubic centimeters, are pipetted into separate titration flasks. And now students, another very important piece of information that I want to give you over here is that usually when we are carrying out a titration, we will take the solution with the unknown concentration into the titration flask. Majority of the time that is the usual practice. But over here we have taken to our titration flask oxalic acid, which is our primary standard we know the concentration of. Now oxalic acid is going to be in the titration flask, while the potassium permanganate, the solution which we don't know the concentration of accurately, in the burette. And why do we do this? One of the reasons is, students, when we are heating this reaction mixture here to about 60 degrees Celsius, if potassium permanganate solution is present here, then it can undergo decomposition. Potassium permanganate undergoes decomposition in sunlight as well as in heat. So to avoid prolonged heating, converting potassium permanganate or making potassium permanganate undergo decomposition, to avoid that, we will have the potassium permanganate in the burette. If it is present in the titration flask initially, then it will undergo decomposition as we heat it for a long period of time. So to avoid this, we have taken oxalic acid into the titration flask. And when we were measuring exactly 25 cubic centimeters of oxalic acid, we used a pipette because we need to be very sure of the volume of oxalic acid we take into the titration flask. Whenever we are carrying out titration, students, we usually use volumetric equipment to measure different volumes so that we can be very sure of the volume of that solution we have taken into the titration flask. So then we can be very sure of the number of moles of that solution in the titration flask. Since it's a standard solution, we know exactly the concentration of the standard solution. And if we use a pipette to transfer 25 cubic centimeters, we can be very sure of the volume that is present in the titration flask. So if you know the concentration and the volume very accurately, we can be very sure of the number of moles that is in the titration flask. Dilute sulfuric acid. Around 15 cubic centimeters of sulfuric acid is added to each flask and the mixture is heated to approximately 60 cubic centimeters. The titration is performed using potassium permanganate solution from the burette. The process is repeated thrice, ensuring that the difference in burette readings at the end point is less than 0.1 cubic centimeters. This means the value of volume readings obtained from titration is used for the final subsequent calculation. So we are using the mean value of the titer volumes. So students, what this paragraph mentions is that we will be carrying out 3 titrations. So we are repeating the same titration thrice. Each time we are going to note down the volume of potassium permanganate that was required to obtain the endpoint. And when we are repeating titrations like this, the titer volumes or the volume of potassium permanganate that was spent to obtain the endpoint should be very similar. In fact, the volume of each trial should only differ from one another with a volume of 0.1 cubic centimeters. If the difference is greater than 0.1 cubic centimeters, let's say 0.3, 0.4 cubic centimeters of a difference is there, at that point the trial that shows an anomaly or trial that shows a larger increase of volume or larger decrease of volume is going to be rejected. More closely related titer values will only be considered when we are calculating our mean titer volume. That means the average volume of potassium permanganate that was used for obtaining the endpoint. So let's say we carried out 3 trials like this and we obtained V1, V2 and V3. So between any 2 readings, the difference should not be greater than 0.1. And after obtaining 3 volume readings like this, we can add the 3 volume readings together and divide it by 3 to obtain our mean titer volume. Mean titer volume means mean or average volume of potassium permanganate that was used to obtain the endpoint. So let's say when we add V1, V2 and V3 and divide by 3, the mean titer volume that you obtained was V cubic centimeters. So this is the number of milliliters or cubic centimeters of potassium permanganate on average that was spent on a titration. And then we very clearly know the concentration of oxalic acid that was used in this titration. Oxalic acid was taken into the titration flask and the concentration of the oxalic acid was 0.05 moles per decimeters cube, and we measured exactly 25 cubic centimeters of it. So then this way we can calculate the number of moles of oxalic acid that was present in that titration flask. So just to give you an idea, in the titration flask we had 25 cubic centimeters of oxalic acid. We can convert it into decimeters cube, that is going to be then 25 divided by 1000 decimeters cube. And over here the concentration of oxalic acid is going to be 0.05 moles per decimeters cube. We will indicate it with capital M. So since we know concentration is equal to number of moles divided by volume, if you need to find out the number of moles, we can rearrange this equation to C multiplied by V, concentration multiplied by volume. So we know the concentration, we know the volume. So if you multiply concentration and volume, you get to this expression. So this is the number of moles or amount of oxalic acid in titration flask. Reactions related to the titration. We have written this equation earlier. Now this is the reaction or ionic equation for the reaction. And you can see by observing the reaction ratio that oxalic acid to permanganate ion ratio is going to be 5:2. 5:2. Now we have already found out the number of moles of oxalic acid that we used. And we know the ratio between oxalic acid and permanganate ions. So if you know all of this information, we can calculate the number of moles of permanganate ions that are going to be needed to react with this many moles of oxalic acid. So this is the number of moles of oxalic acid that was in the titration flask. To react with exactly this many moles of oxalic acid, we can find out how many potassium permanganate or permanganate ions are needed. And we know the ratio. The amount of KMnO4 that is needed to react with oxalic acid can be found in this way. So this is the number of moles of oxalic acid that is there, and the reaction ratio is 5:2. So if you divide this number by 5 multiplied by 2, you will get to the number of moles of potassium permanganate that is needed to react with that specific amount of oxalic acid. So we obtain that with the use of this reaction ratio. Volume of permanganate ions solution is V cubic centimeters. We calculated that earlier. If each trial has V1, V2 and V3 volumes, we calculate the mean volume. Mean volume is going to be capital V cubic centimeters. So this many moles of potassium permanganate is present in a V volume. So now we know the number of moles and we know the volume. Only thing that we don't know is concentration. Concentration is equal to number of moles divided by volume, isn't it? So then after making very sure we know what we are talking about, especially in volume V, we have this many moles of potassium permanganate. So at that point we can calculate potassium permanganate concentration by taking the number of moles divided by volume. So this is going to be the number of moles and V is going to be the volume, but V was given in cubic centimeters. So if you want to convert into cubic decimeters, you have to divide by 1000. But V is already under the division mark or division line here. So when we try to divide V again by 1000, that 1000 comes above the dividing line. So you can see at that point, this 1000 and this 1000 will cancel off. And the final answer is going to be 0.5 divided by V moles per decimeters cube. So this is our expression for the concentration of potassium permanganate solution. So we have now derived an expression for the potassium permanganate solution. Using 0.05 moles per decimeters cube oxalic acid solution as a primary standard, the concentration of the secondary standard KMnO4 minus aqueous solution can be determined through a titration to be 0.5 moles, 0.5 divided by 2, 0.5 divided by V moles per decimeters cube, where V is the mean titration volume. V is the mean titration volume. So we have now developed an expression for our concentration of permanganate ions. So students, this is how the titration is going to be carried out. Let's move on to the next slide. Equipment and chemicals required. So we'll be using the equipment and chemicals that is mentioned here, students. We'll be using titration flask, volumetric flask, burettes, pipettes, watch glasses, porcelain tiles. Apart from that, we'll be using oxalic acid solution, which is 0.05 moles per decimeter cube concentration, and 0.02 moles per concentrated potassium permanganate solution. But this is just an approximate concentration. We are going to be finding the concentration of it properly later on. And then we'll be using 2 moles per decimeter cube concentrated sulfuric acid as well as distilled water. Preparation of 0.05 moles per decimeter cube oxalic acid solution as a primary standard, students. So we are going to be using oxalic acid. Mainly if potassium oxalate is not available, we can use oxalic acid or sodium oxalate as an alternative. So in this case, we will be using oxalic acid. To prepare 250 cubic centimeters of 0.05 moles per decimeter cube concentrated oxalic acid aqueous solution, we can carry out the following calculation. We know the concentration and the volume that we need to prepare of the solution. So concentration is 0.05 moles and the volume is 250 milliliters. So when you're converting milliliters into decimeters cube, 250 divided by 1000 is written here. So this is the expression for the number of moles. This is the expression for the number of moles of oxalic acid that we should have in our primary standard solution. And when you solve that equation, the number of moles is 0.0125 moles. And oxalic acid molar mass, or mass of just 1 mole, is 90 grams. But if you communicate it as molar mass, it should be 90 grams per mole. The amount of oxalic acid that we should measure is the number of moles multiplied by its molar mass. So we have altogether 0.0125 moles multiplied by oxalic acid molar mass, 90 grams per mole, 90 grams per mole. There should be a grams here, students. Let me add that, 90 grams per mole. So you can see per mole and mole cancel off and the answer will be obtained in grams. So 1.125 grams should be measured. So to prepare oxalic acid solution with this concentration and to prepare 250 cubic centimeters of that solution, we will need to measure 1.125 grams of oxalic acid solid. Place the clean watch glass on the electronic balance and tare the reading. First of all, you turn on the balance, you place a clean watch glass on the balance and then use the tare function to get to a 0 reading. And then we precisely measure this many grams, 1.125 grams of oxalic acid. We will measure it into the watch glass and then we will transfer the measured crystals into 250 cubic centimeters of volumetric flask using a funnel, and then a suitable amount of distilled water is going to be added to the volumetric flask, and we are going to try and dissolve all of the oxalic acid crystals we have added to our volumetric flask with the use of distilled water. And after it is completely dissolved, we will add more distilled water to reach the 250 cubic centimeter mark, or in other words, the calibration mark that is seen in the volumetric flask. And after we add water all the way up to the calibration mark, we can stopper the volumetric flask. That means we can place a stopper on the volumetric flask, and then we can rotate the volumetric flask a few times to mix the solution really well to prepare a homogeneous solution. So a diagram of this is given here in this slide. We will be measuring all of our oxalic acid crystals into a watch glass. You can see the watch glass here, and on the watch glass we have the oxalic acid crystals, and we'll be using a wash bottle and a funnel, and we are going to wash down these crystals directly into a volumetric flask. So after washing these solid into the volumetric flask, then we will wash this watch glass with distilled water. Both sides of the watch glass should be washed, and then you will be washing the inside of the funnel as well as the tip of the funnel as well. And then before we top up the volumetric flask with water, we will dissolve the solid in the volumetric flask here, and after that, after all the solid is dissolved only, we will be adding water all the way up to the calibration mark. You can see a calibration mark here as well as here. So we'll add water all the way up to the calibration mark in such a way that the bottom of the meniscus of the solution aligns with the calibration mark as indicated here. Now we can carry out the same few steps when preparing potassium permanganate solution as well. And the concentration of the potassium permanganate solution and the volume of it is known to us. So just like what we did in the previous instance, we can calculate first the number of moles of potassium permanganate that we need to have in our solution. So we know the concentration, we know the volume. So concentration multiplied by the volume will give us the number of moles of potassium permanganate that should be in the solution. In this case, it happens to be 0.005. And we know the molar mass of potassium permanganate, 158 grams per mole. So we know the number of moles, we know the molar mass. If you multiply them, you can see per mole over here, and mole cancels off, leaving behind just grams. So this is the gram value, or this is the mass of potassium permanganate that we should measure to prepare 250 cubic centimeters of 0.02 moles per decimeter cube concentrated potassium permanganate solution. So now we have measured, or we have calculated the mass of potassium permanganate we need to measure in order to prepare our potassium permanganate solution. So like in the previous instance, we will place our watch glass on the balance, and then we'll use a tare function, and then we'll measure approximately around 0.8. The correct measurement would be 0.79, but we are trying to prepare a potassium permanganate solution with approximately 0.02 moles per decimeter cube concentration. So at that point, we don't have to be very precise. Even if the value is somewhere around 0.8, that is okay, because potassium permanganate is not a primary standard, and we are not sure of the concentration of the solution we are preparing as well. So that is why we say approximately 0.02. So students, we don't have to measure exactly 0.79. It can be 0.8 as well. And then we can use 0.8 grams instead of 0.79 grams as intended, as I mentioned earlier. And then we can transfer this weighed potassium permanganate crystals into 250 cubic centimeter volumetric flask with the use of a funnel and a wash bottle, like I mentioned earlier. And the next few steps are going to resemble the previous process, which I can explain here. So after measuring 0.8 grams of potassium permanganate, with the help of a wash bottle and a funnel, we will add these, or we will wash these solid crystals into our titration flask. And when you do that, majority of the solid will come into the titration flask, and at one point all of the solid will completely be washed off of the watch glass. And after that, we will use the wash bottle to thoroughly wash the watch glass. Both sides of the watch glass will be washed, and then the funnel, inside of the funnel, will also be washed like we did in the previous instance, and all of the water will be added into our volumetric flask. So at that point, the volumetric flask volume is going to be somewhere around this range. And then if there are any solid traces remaining, you will hold the volumetric flask from the neck area, not this narrow neck part, from the wider base area, and we will swirl it around until all the solid is dissolved. And then we will add water all the way up to the calibration mark. And we need to make sure the bottom end of the meniscus aligns perfectly well with the calibration mark. And after that, we will place a stopper, and then we will turn the volumetric flask upside down a few times to make sure the solution is mixed well and a homogeneous solution is prepared. So how do we identify the endpoint of a titration? Very clearly, in this case, we know the titration is from clear to pink. So how do we identify this endpoint? When we are carrying out the titration, a noticeable color change from colorless to pink is observed, from colorless to pink. To achieve the endpoint, it is crucial for the pink color to persist for 15 to 29 or 30 seconds. You should have this pink color remaining in the medium for a while. If it disappears after about 10-20 seconds, that means the potassium permanganate that gave that pink color has again reacted with the remaining amount of oxalic acid in the medium. So as the oxalic acid concentration goes down in the medium students, anyway the reaction rate further decreases. That's why it is always better to keep the temperature approximately around 60 degrees Celsius. So when the temperature is high, the reaction rate is going to be greater. So in the event that the pink color turns colorless, the titration flask should be gently heated again and titration process should be repeated. So if the color disappears, then again we have to gently heat the reaction mixture and bring it about to 6 degrees Celsius, and then add another drop of potassium permanganate and see even if that color is going to disappear. So if that color persists, then that is your endpoint, right? So you have to be very careful when you're obtaining the endpoint here, because sometimes you will think you have observed the endpoint, but after a while, after about 10-30 seconds, you will see the color disappearing again. That means potassium permanganate has further reacted. So this indicates that the endpoint is not yet reached. So again, you elevate the temperature to about 60 degrees Celsius and add another drop of potassium permanganate to see if that potassium permanganate drop's color disappears. If it doesn't disappear, that means you have obtained the endpoint. If it does disappear, you have to keep doing the titration until you obtain your endpoint. Explanation for the reasons why reaction between oxalate anion and permanganate is carried out at a temperature of about 60 degrees Celsius in acidic medium. So let's go through this. Particles need certain level of kinetic energy to initiate a reaction, known as activation energy. We all know this. Regardless of what type of reaction it is, particles do need to have a minimum amount of energy to take part in the reaction, and that is known as our activation energy. Only the particles with this energy or higher will undergo a reaction. Particles that possess a lower amount of energy than this energy will not undergo the reaction. However, not all particles in the system possess this sufficient kinetic energy at room temperature, leading to a very slow reaction. To address this, system's temperature is raised to 60 degrees Celsius. Now students, you might have learned about Maxwell-Boltzmann distribution. If you take a look at Maxwell-Boltzmann distribution, or if you take a system, particles in a system will have an energy distribution like this. Now this axis is going to be energy and the y-axis is going to be the fraction of particles with that particular amount of energy. Now majority of the time you can see there's going to be only a small portion of particles that will have very low amount of energy, and a very small portion of particles will have really high amount of energy, and majority of the particles will have average amount of energy. But for a given reaction, students, there's going to be an activation energy. Let's say the activation energy is somewhere around here. Let's say the activation energy is somewhere around here. Bear with me just a second. This is our activation energy. So all of these particles that have lower energy than the activation energy can't take part in the reaction. Only this small fraction of particles, that have energy equal to or greater than the activation energy actually can take part in the reaction. However, students, if you increase the temperature, then majority of the particles will have a greater amount of energy than the activation energy, because this average energy value will shift to a greater energy. You can see the distribution curve has now shifted more towards the right, and the average energy value of the system has increased, because when we provide heat to the system, average heat in the system increases, or average energy in the system increases, because you are providing energy into the system. So if you take the particles and particles average energy also has increased, and majority of the particles now have a high amount of energy. So you can now see in the new temperature, let's say this is 6 degrees Celsius. In the new temperature, there will be greater number of particles, or greater fraction of particles that has more than the activation energy. So now a great number of particles can take part in the reaction. Activation energy is not the only thing that is important when you're talking about the energy when you're talking about successful collisions. One thing is activation energy, or energy, minimum amount of energy needed for a successful collision should be there in particles. But apart from that, you also need correct orientation and collisions as well. But without this correct amount of energy, particles cannot engage in any successful collision. Even if the orientation is correct in the collision, if they don't have the correct activation energy or correct energy, at that point it will not result in a successful reaction. So all of these particles that have a low amount of energy than the activation energy will not result in producing products. They will not undergo the reaction. But now when you increase the temperature, a greater fraction of particles will have higher amount of energy than the activation energy. So all of these particles that I have indicated in this red shaded area is now capable of taking part in the reaction, and that amount of particles is much greater than the blue shaded area. So this is why the reaction rate increases, because number of particles that can take part in the reaction is much greater. As the temperature increases, the particle speed and the kinetic energy rises. Consequently, the activation energy threshold is met by a greater number of particles, enhancing the frequency of collisions between particles in a given unit of time, as well as enhancing the number of successful collisions due to the energy requirement being met. The overall acceleration of particles of motion contributes to increased reaction rate. So this is the reason, students, why we increase the temperature. Higher the temperature, higher the number of particles that exceed the activation energy, and higher the number of successful collisions that take place in a given period of time. So because of that, the rate of the reaction increases. Redox reactions between potassium oxalate and potassium dichromate. Potassium oxalate and potassium dichromate, not potassium chromate. There is a small correction here. Potassium dichromate, C2 or K2Cr2O7, potassium dichromate. The reaction between the reaction in dichromate in potassium dichromate act as an oxidizing agent in acidic medium. So in potassium dichromate we have dichromate ions, and the dichromate ion is a orange color ion. So it can undergo a reduction while oxidizing something else. So we have shown the reduction reaction here. It undergoes reduction from +6 to +4. This is a reduction very clearly. So what is undergoing oxidation here? The oxalate anion undergoes a oxidation. So that reaction is also given here. Oxalate anion undergoes an oxidation. So oxidation number of oxalate anion is +3. It goes to +4. So this is a oxidation. So you need to know which species is going to undergo oxidation. In this case, oxalate anion. Which species is going to undergo reduction? In this case, dichromate ion. And over here we have the half equations written, students. Again, writing half equations shouldn't be difficult to any of you by now, especially potassium permanganate half equation and potassium dichromate half equation. We have written them quite a number of times over the past experiments, as well as I'm quite sure at school as well you have written these equations quite a number of times. So by now you should be very good at writing these equations. And again, oxalate ion has turned into carbon dioxide and electrons. So you can see in the first reaction electrons are taken in, it is a reduction. In the second reaction electrons are given out, it is an oxidation. So we have reaction number 1, reaction number 2. But the number of electrons in both of the reactions are not a match. In the first reaction you can see 6 electrons are taken in. In the second reaction only 2 electrons are given out. So to make sure the electrons are a match, we can multiply the second reaction by 3. And then the electrons will be 6 here. So when you multiply the entire equation by 3, number of electrons will also get multiplied by 3. And then since the electrons are a match at that point, we can add the 2 reactions together. So reaction number 1 added to reaction number 2, that is multiplied by 3. It's going to give us our main ionic equation for the reaction that is taking place. So orange color dichromate ions that are orange in color are going to get converted into chromium 3+. Now students, chromium 3+ ions in aqueous medium majority of the time appears green due to complexes that chromium 3+ make with water ligands and other ligands that are available in acidic medium like sulfate ligands. So chromium 3+ ions in aqueous medium, due to forming complexes with water and sulfate ligands that are available in aqueous medium, it will form a green color complex here. And apart from that, water and carbon dioxide will also be formed. So color change that is observed here is going to be from orange to green. And since oxalic acid is colorless, or potassium oxalate in this case is colorless, so we will not necessarily see a color coming into the medium through oxalate anions. Only dichromate ions and chromium 3+ ions will give off the colors in this reaction. So when you're standardizing our potassium dichromate solution using potassium oxalate, we can use a setup like this. Potassium dichromate can be taken into our burette, and then oxalate can be in the titration flask. So this is one way that we can do it. And students, when it comes to potassium dichromate in itself is a primary standard. So you wouldn't need to standardize potassium dichromate with the use of potassium oxalate. However, if you happen to not know the concentration of a solution you have prepared and you have forgotten the concentration, at that point you can carry out a titration like this to find its concentration. But since potassium dichromate in itself is a primary standard, you can prepare a primary standard from scratch. If you are trying to titrate and find out potassium dichromate solution, this setup is one way that you can find out the concentration of potassium dichromate. Standardization of potassium dichromate solution using potassium oxalate primary standard. We can take 25 cubic centimeters of oxalic acid into a titration flask, and then we acidify the titration flask's contents using sulfuric acid, and then titrate the content with potassium dichromate solution. And then we will determine the volume of potassium dichromate that is needed to obtain the endpoint. The volume of potassium dichromate consumed at the endpoint is, let's say, V cubic centimeters. If that is the case, students, through a calculation like we did in the past, they can find the number of moles of potassium oxalate that was present, because we have measured 25 cubic centimeters of it and taken into the titration flask. So we know the potassium oxalate concentration if the potassium oxalate concentration is 0.05 moles per decimeters cube. And through this reaction, we know the ratio between dichromate ions to oxalic or oxalate ion ratio is going to be 1:3. 1:3. So in this case, we have written oxalic acid and then dichromate, so then it's going to be 3:1. With 3 oxalate anions, 1 dichromate ion will be reacted. So because of that, we can say potassium oxalate to potassium dichromate ratio is 3:1. So now we know the number of moles of oxalate ions or potassium oxalate. Then we can find out that potassium dichromate is going to be 1/3 the value of the number of moles of potassium oxalate. You can see potassium oxalate to dichromate is 3:1. If you know oxalate number of moles, 1/3 of that particular number of moles is going to be the number of moles of potassium dichromate. And that's what we have done here. So this is the number of moles of potassium dichromate, and this is the volume of potassium dichromate. This many moles were present in. So if you know the number of moles and the volume, you can divide the number of moles by the volume. Now volume is in cubic centimeters, so volume should also be divided by 1000. And when you do that, it turns into this. So students, if you know the number of moles and the volume, you can derive an expression for the concentration of potassium dichromate. After doing that, please note that the concentration of potassium dichromate can be determined through the titration mentioned above. However, as potassium dichromate is a primary standard, its concentration can also be calculated by preparing a solution with a known mass and a volume of it. If you know the mass of potassium dichromate you have taken and the volume of it, since potassium dichromate is a primary standard, you can calculate its concentration. If you happen to not know the mass or the volume, and if you happen to have forgotten the potassium dichromate solution's concentration, then through a calculation or through titration and then a calculation, you can find its concentration. Observing these reactions offer insights into the reaction ratios between ferrous oxalate and acidic potassium permanganate, as well as ferrous oxalate and acidic potassium dichromate. This comparative analysis helps us uncover the specific stoichiometric relationship in these chemical processes. So we are now going to take a look at what will happen if we use ferrous oxalate and carry out a reaction between ferrous oxalate and acidified potassium permanganate and ferrous oxalate and acidified potassium dichromate. Now, what is so important or what is so interesting about ferrous oxalate here? Now, potassium permanganate in acidic medium is an oxidizing agent. Now, ferrous oxalate contains two things that can get oxidized. Ferrous can be oxidized to ferric. Oxalate and iron can get oxidized into carbon dioxide. So, two things in this ferrous oxalate can get oxidized by just potassium permanganate or potassium dichromate in acidic medium. So, let's take a look at that. Acidic permanganate ion redox reactions with ferrous oxalate. Oxidation of ferrous and oxalate ions in ferrous oxalate to Fe3 plus and carbon dioxide respectively can be seen here. Here permanganate ions will be reduced to Mn2 plus. So you can see, like I mentioned in the previous slide, ferrous got turned into ferric. This is an oxidation, students. Oxidation. Electrons are released. Each ferrous oxalate contains one ferrous ion and one oxalate ion. So each time you react potassium permanganate with ferrous oxalate, one ferrous will turn into ferric and one oxalate ion will turn into carbon dioxide, two carbon dioxides. So these two oxidation reactions will happen with each ferrous oxalate. Each ferrous oxalate will include both of these reactions, and both of those reactions are oxidation reactions. So if you join them and write, you can just write ferrous oxalate aqueous will turn into ferric and carbon dioxide, and 3 electrons will be released in this reduction reaction. So, in this oxidation reaction. So this is also an oxidation reaction, right? This is a oxidation. And the only reduction reaction that is in the medium right now is potassium permanganate. In acidic medium, potassium permanganate undergoes a reduction to Mn2 plus. And we know the equation for that. So the oxidation releases 3 electrons, reduction takes in 5 electrons. So the number of electrons that are given out and taken in are not a match. So in order to make sure that both of these electrons that are released and taken in are the same, we will have to multiply the third reaction by 5 and fourth reaction by 3. When you do that, on both sides the electron number will be 15. You need to multiply the entire equation. When you do that, you will get to your final equation, which is going to be 5 ferrous oxalate, 3 permanganate, 24 H plus turn into 5 ferric, 10 carbon dioxide and 3 Mn2 plus and 12 water. So this is going to be your final ionic equation. And after observing that, we can note down the reaction ratio between ferrous oxalate and permanganate ions. Ferrous oxalate to permanganate ratio. Ferrous oxalate to permanganate ratio is 3:2. 3:2. So that is something that we need to keep in mind. And then we have potassium dichromate reacting with ferrous oxalate. Just like I mentioned earlier, ferrous can get oxidized into ferric. Even acidified potassium dichromate is an oxidizing agent, students. So in there, ferrous can turn into ferric and oxalate can turn into carbon dioxide. Both are going to be oxidation reactions. So we can combine the two, and like we did earlier, write this equation. Ferrous oxalate turns into ferric and carbon dioxide. So this is going to be the overall reaction when one ferrous oxalate gets oxidized. So ferrous oxalate oxidizes to Fe3 plus carbon dioxide. So this is the oxidation reaction. Only reducing or reduction reaction that you see in this particular reaction mix is going to be when dichromate turns into chromium 3 plus and water. So you can join them two and write the final equation. But before you do, you need to notice that in the oxidation reaction there are 3 electrons removed, and in the reduction reaction there are 5 electrons taken in. So in the reduction, since the electron number is greater, you need to multiply reaction number 3 by 2 and then add it to reaction number 4. So that's what we have done here. Reaction number 3 was multiplied by 2 and then added to 4. When you do that, we get this equation. 2 ferrous oxalate and 1 dichromate ion will react with H plus in the medium and form 2 ferric, 4 carbon dioxide and chromium 3 plus and water. The main interest here is the reaction ratio. So ferrous oxalate C2O4 to chromium or dichromate ion, actually not chromium, dichromate ion is going to be 2:1 students. With each dichromate ion, there will be 2 ferrous oxalate reacting with it. So stoichiometry between ferrous oxalate and dichromate is 2:1 with 2 ferrous oxalate, 1 dichromate. But the stoichiometry when ferrous oxalate is replaced by oxalic acid, we saw this earlier, it was 3:1. Oxalic acid to dichromate ratio was 3:1. So you can see a difference in the reaction ratios or stoichiometric ratios. This is because ferrous oxalate has ferrous that can undergo oxidation apart from oxalate ions. Over here, hydrogen doesn't undergo oxidation, only oxalate ion does. So that is why the reaction ratio or stoichiometric ratio is different here. And lastly, we take a look at the stoichiometry between oxalic acid and potassium permanganate. We have observed this earlier as well, students. We have taken a look at this reaction initially in a previous slide. So we know the reaction ratio between oxalate ion and permanganate ion is going to be 5:2, right? This equation was developed earlier. We have done that part earlier. So we know the stoichiometry between oxalate or oxalic acid and permanganate is 5:2. When oxalic acid is replaced with ferrous oxalate, then the ratio is 5:3. 5:3. Again, the reason for this is apart from the oxalate ion that can undergo oxidation here, ferrous is also present when ferrous oxalate is used instead of oxalic acid. So you need to observe these reaction ratios or stoichiometric ratios and develop a good enough understanding of what is happening when we use oxalic acid with permanganate ions and ferrous oxalate with permanganate ions. So with this, students, we have now provided you with enough information and we have elevated your knowledge up to a level that you can use it to understand what happens when we are reacting potassium permanganate or potassium dichromate with an oxalate ion. So usually these reactions will take place in acidic medium. Now students, after going through all of these theory parts, I hope you have developed a sufficient understanding of what type of reactions take place between acidified potassium permanganate and oxalate ions and acidified potassium dichromate and oxalate ions. So with this new understanding, we can now move on to the lab and actually conduct our experiment. So let's move on to the lab now. GCE Advanced Level Chemistry Practical number 20. Determination of the concentration of a potassium permanganate solution with the use of standard acidified potassium oxalate solution. In this practical, we aim to give you the necessary knowledge on how to prepare a known concentration of a standard solution, and then we will move on to how we can determine the concentration of a permanganate ion solution through a redox titration. Now, let's move on to the reagents we will be needing for this practical. These are the reagents and the equipment we will be using for this practical. We will be needing a beaker, a funnel, a 250 milliliter volumetric flask. We will be using a potassium permanganate solution with approximate concentration of around 0.02 moles per decimeters cube. We will be using a wash bottle, a pipette, and a pipette filler. We will be using potassium oxalate, the white powder you see here. We will be using a watch glass to measure the potassium oxalate, spatula, 3 titration flasks, a retort stand that you see over here. We will be using a spirit burner with a tripod and a wire mesh. And finally, to carry out the titration, we will be using a burette as well. To measure the mass of the solid, we will be using a digital balance that we have here. So those are the equipment and the reagents we will be using for this practical. Let's move on to our practical. Now, let's move on to our practical and start weighing potassium oxalate. But before we get on with it, I would like to let you know why we have to titrate a potassium permanganate solution before we use it in other titrations. Now, as you may know, potassium permanganate is not considered a primary standard. Why is it not considered a primary standard solution? Mainly, potassium permanganate is not obtained in a very pure form. It contains a little bit of KMnO4, which takes away from the quality of a primary standard. As well as when you are leaving potassium permanganate solution after you prepare it for a while, if you leave it to stand for a while, it has the ability of getting decomposed if it is exposed to sunlight. So we do not want a standard solution formed with such substance. So we will move on to other substances like potassium oxalate over here, which has a high purity, which is a very stable compound, and it has a very good equivalent mass, and it is relatively cheap, and we can actually find it with relative ease. So we will be using potassium oxalate as a primary standard in this practical. However, potassium permanganate is a desirable titrant because it will give you a color change. It acts as a self-indicator, so it will give you a nice color change at the end of titration, and we prefer to use potassium permanganate. If it is standardized, we can use it for titrations to determine the endpoint without having to add an additional indicator. With that knowledge, Let's move on to measuring the mass of potassium oxalate needed for this practical. We need to prepare a potassium oxalate solution with a concentration of 0.05 moles per decimeters cube, and the volume of the solution that we are preparing is 250 cubic centimeters. So we know concentration is equal to number of moles divided by the volume. Using that equation, we can find out the number of moles of potassium oxalate that we will be needing for this practical. And then if you know the molar mass of potassium oxalate, you can use the number of moles and the molar mass and calculate the mass of potassium oxalate needed for this practical. So we have already done the calculation. The mass of potassium oxalate that we need for this titration is 2.08 grams. Let's move on to measuring that 2.08 grams. We will turn on the digital balance we have here, and we will use a watch glass to measure the potassium oxalate. So we will place the watch glass over here. We actually do not need to know the mass of the watch glass because since we are using a digital balance over here, we have the option of removing that weight or by tearing, using the tear function over here in the digital balance. Now the mass of the watch glass is disregarded. You can see the scale reads 0.00. Now I will take potassium oxalate and take a spatula full of potassium oxalate and transfer 2.08 grams onto the watch glass. You have to take your time and carefully measure exactly 2.08 grams. As you can see, we have now measured 2.08 grams of potassium oxalate. We can now move on to transferring this 2.08 grams of potassium oxalate onto a volumetric flask. And while I was measuring, I got reminded of a very important characteristic that a primary standard should have. That is, primary standards should not be hygroscopic, which means it should not absorb water from the surrounding or from the atmosphere. Normally, whenever you are weighing a hygroscopic substance, you can see that it absorbs moisture from the air and it starts to dissolve on the watch glass itself. This is not a good feature for a primary standard, so anything that is hygroscopic is not a good choice for a primary standard. And potassium oxalate is not hygroscopic, so that is actually perfect for a primary standard. So with that information, now we have measured 2.08 grams of potassium oxalate. We will no longer need the balance now, we'll keep it aside. And now we will move on to transferring this solid onto our volumetric flask. Let's move the balance out of our way. To transfer this solid completely onto this volumetric flask, we will be using a funnel. We will open the volumetric flask, we will remove the stopper, And we will place the funnel on the volumetric flask like so. And now I will transfer this solid onto the volumetric flask with the use of a wash bottle and some distilled water. So you have to wash the solid onto the funnel, making sure no solid remains on the watch glass. After you wash one side of the watch glass, you have to turn it around and wash the underside of the watch glass. Otherwise, there could be some residual amounts of solids remaining there. So once you do this, all of the solid would be washed and transferred onto our volumetric flask. Let's move on and swirl this volumetric flask around. Try to dissolve all of the solid that we have here before we add more water onto it. You can see when I swirl it around a little bit, most of the solid dissolved. Now you can gradually start to add water. Now all of the solid has completely dissolved. Now let's add water little by little, and we'll make sure that we add water only up to this 250 gradient line that you see over here. So the meniscus of the solution should align with the gradient line that you see over here. So when you're adding the last bit of your distilled water to make this solution, please make sure to raise the volumetric flask up to your eye level so that you can see the gradient line at your eye level. And then you can slowly start to add water very close to the gradient line, and then we can move on to a dropper to more carefully add water drop by drop. Now I will be adding water drop by drop onto this volumetric flask. Now the volumetric flask gradient line and the bottom level of the meniscus of the solution perfectly aligns. So if you are unable to hold the volumetric flask straight, what you can do is you can place it on a table, and you will have to bring your eye level down to that gradient line, and then observe if you have actually prepared the standard solution properly. Right. So now we can see very clearly that the gradient line and the bottom level of the meniscus of solution is in perfect alignment. If you have added a little bit less water, or if you have added a little bit more water, you would have actually not created a perfect standard solution. Especially if you have added additional amount of water, you have to discard this entire solution and you have to start over. So after preparing the solution like that, so we are not yet done. We have to close the stopper quite tightly, making sure there won't be any spillage. And then you can start mixing it around, but since there's a lot of water filled over here, the best way to mix it is close the stopper really tightly and then turn this volumetric flask upside down. You can do it a couple of times to make sure that all the contents are properly mixed. Once you have turned it upside down a few times, like so, you can be sure that everything in here is now properly mixed and you have prepared a homogeneous solution. So this is how we make our standard solution of potassium oxalate with the concentration of 0.02 moles per decimeters cube. Let's move on to our next step. Whenever we are doing a titration, we have to know how to use a burette. So let's first focus on how we can clean a burette and then how we are going to fill a burette up. So what we have here is a burette connected to its retort stand, and before we use this burette, we have to make sure that it is washed with distilled water, and then we have to wash it again with the solution that you're going to fill into the burette. This is to make sure that the droplets of water that is remaining inside the burette does not dilute the solution that is being added to the burette. So to make sure that it is not going to change its concentration, whatever the solution that we add here, that it is not going to change the concentration, we will have to wash this burette twice, once with distilled water, and second time we are going to use the solution that we are adding to this burette, and we are going to wash it again with that solution. So let's move on to washing this burette. Whenever you are trying to use a burette in a lab environment, one of the mistakes that I have seen a lot of students make is that they will keep the burette and the retort stand on the lab desk itself, and then they will place a funnel on the burette which is over their head, and they will take the solution and lift it again over their heads, which is a bit of a risk in the lab environment, because if you spill it while it's over your head, it will directly get spilled on your face. So we will not do that whenever you are filling a burette. So what you do is you find a stool or a table that is shorter than the lab table, and we will move the burette onto that table. So now the opening of the burette is going to be below your eye level. So now you can take a funnel and place the funnel on the opening of the burette and wash or actually transfer some water onto the burette. While doing so, please make sure the burette tap is closed. Now I will be adding a little bit of water onto the burette. After transferring some water, I'll transfer some more. After transferring some water onto the burette, to show you all what needs to be done, I'll bring it back onto the lab table. You will take a beaker and open this tap rapidly, making sure the tip of the burette is also cleaned with distilled water. And then we will remove the burette from the retort stand, and then we'll make sure that we don't spill a lot of water, and then we'll turn the burette sideways and wash the interior walls of the burette.
by rotating the burette like this. So while doing this, you can remove the water onto another beaker to discard the water that was used to wash the burette. You can open this end to make sure all of the water in the burette is removed. So that is how you would normally wash a burette using distilled water. This is just the first step. After using water and washing it, we will have to use the solution that is going to be filled into this burette and wash this burette again with that solution. So let's move on to that. So in order to do that, I will take the retort again and fix this burette like this. And then transfer some of the solution that will be used to titrate, or that will be used to fill this burette in the titration. And now again, I will have to take this burette onto a stool that is shorter than the table over here. And I will use a funnel again to transfer some of this solution into this burette. Again, when you're transferring any liquid into the burette, make sure that the tap or the burette tap is completely closed. Otherwise, while you add, you will be making a spill due to the tap being open. Now I will move this back onto my table. Just like in the previous setup, I will open this tap and make sure that the tip of the burette is also fully cleaned. So I will open it rapidly, allow some solution to run through. So now I know even the tip is completely washed. Afterwards, I can remove this burette from the stand and continue to wash it like I washed it before. So let's remove the burette from the stand. Now, like in the previous example, I will be turning this sideways like this and making sure the entire interior surface of the burette is completely washed properly with the solution that is about to be filled into the burette. With this, the washing of the burette is complete. One additional step would be to open the burette and let the remainder of the solution run through. Now, burette is completely washed. We can move on to the experiment. After washing the burette, we will again fix it onto our burette's retort stand, and we will move it back onto a shorter table. Since the washing of the burette is complete, now we will be filling up the burette with a solution that goes in the burette, which is 0.02 moles per decimeters cube concentrated potassium permanganate solution. So let's add that solution onto the burette. So for that we will require a funnel. We will place the funnel over here. So after placing the funnel, let's take another beaker and transfer some of the liquid or the sample that we need to fill into the burette. Let's take about little over 50 milliliters because the burette can hold only 50 cubic centimeters. And now, after making sure the burette tap is closed, we will start adding the potassium permanganate solution into the burette. When you are filling a burette, please make sure initially when you're adding the solution to add the solution over the zero line. The reason for this will be clear to you in just a second. After adding the potassium permanganate solution over the zero line, you can see that this tip of the solution is still empty, or tip of the burette is still empty. So we need to fill that area as well. So what we do is we open this tap rapidly to make sure that area is completely filled. Now I wanted to show that to you. That is why I brought the burette onto the table again. Now we have to make sure we keep it at eye level and bring the solution down onto the zero line. So let's do this together. So in this burette, we have the solution level above the zero line, and we have to make sure that the meniscus of the solution over here aligns with the zero line of the burette. So especially when it comes to a dark colored solution like this, finding the zero line could be difficult if you are doing it in a dark environment. So please make sure that you have some sort of light source behind the burette so that you can place or find where the zero line is easily. So let's open the tap of the burette and bring the solution line down to the zero line. And please notice that I try my best to keep my eye level with the level of the meniscus. This is done to make sure that the meniscus and the zero line are aligning perfectly. The zero line is over here. I'm not sure whether the camera can capture the meniscus, but meniscus is aligning with the zero line that is present in the burette. Right. So now I have removed some solution and made sure the meniscus of the solution is perfectly aligning with the zero line of the burette. With that, we have finished. With that, we have actually now finished filling up and cleaning the burette. Now the burette is set up for our titrations. Now we will be moving on to filling up our titration flasks to carry out the titration. To prepare the solution that is going to be titrated against potassium permanganate solution that we have, we need to measure exactly 25.00 centimeters cube of the potassium oxalate solution that we made earlier. So in order to do that, we need to first wash our pipette. So let's move on ahead and wash our pipette. We need to first of all wash it with a little bit of distilled water to remove any impurities that is currently having, and then we need to wash it again with our potassium oxalate solution. Before we fill this pipette with potassium oxalate solution, we have to do those two things: wash it with distilled water and then wash it with potassium oxalate solution. Let's go on ahead and do that now. Here we have our distilled water. We will take our pipette and use a pipette filler such as this one, and we will press the topmost valve over here and squeeze the pipette filler and try and take in a little bit of water with the use of the second valve that you have over here. As you can see, when I am pressing it down, pipette is getting filled with water. Now, after you have taken in sufficient amount of water into the pipette, we can remove the pipette filler like this, and then we can turn it around and let the water go. After a while, we can let the water go out of the opening of the pipette. Now I have taken distilled water into the pipette once and let it out, making sure that I have washed the interior walls of the pipette with distilled water. All that is left for me to do now is to take our potassium oxalate solution and wash it with our potassium oxalate solution. Let's take a small beaker and take our volumetric flask. Now this is a potassium oxalate solution that we prepared earlier. We have to make sure that you do not put the pipette into the volumetric flask. That is not a good practice. So we will withdraw a small amount of potassium oxalate onto a different beaker. Now let's transfer adequate amount of potassium oxalate onto a small beaker. We'll fix the pipette filler again like so. We'll again squeeze out the air in the pipette filler, and then we'll place the pipette filler into the beaker like this, and we'll draw in some potassium oxalate solution. After taking an adequate amount of the potassium oxalate solution into the pipette, as you can see, I'm keeping my thumb over here to make sure the entire solution doesn't fall back into the beaker. You can take the pipette out and keep it horizontally like this and turn it around, making sure all of the interior walls of the pipette is completely coated with potassium oxalate. Once you are done, you can take another new beaker and discard the solution that you used to wash the interior of the pipette. Now we have completed the washing of our pipette. Now we can move on to taking some amount of solution into this pipette. We'll use this pipette to transfer exactly 25 cubic centimeters of potassium oxalate onto our titration flask. So we will have our titration flask here. Since we have to measure exactly 25.00 cubic centimeters of potassium oxalate, we have to make sure that we use our pipette and then measure exactly 25 cubic centimeters of potassium oxalate. As you can see, with the help of the pipette filler, you are able to measure exactly 25 cubic centimeters. Now, when you are using a pipette filler like this, you have the option of drawing in more water like this, and you can release some water with the help of these two buttons over here. These are actually valves. You can see when I press this valve, it will draw in some water, or actually the solution over here, and when I press the other one, it will allow the solution to run back into the beaker. So while using these two buttons over here in the pipette filler, I will make sure that I draw only up to the gradient line that we have over here. As you can see, the bottom level of the meniscus is in alignment with the gradient line of the pipette. This means that we have measured exactly 25 cubic centimeters of potassium oxalate solution. Now we can safely take this pipette and make sure the tip of the pipette is touching the interior wall of our titration flask, and then we can allow the liquid to run down into the titration flask. Right. After transferring all of the liquid, please make sure not to force this last droplet that is present on the tip of the pipette. This tip is supposed to be there on the pipette because the pipette is calibrated in such a way that this droplet over here on the tip is supposed to remain on the pipette itself. So do not force it onto the titration flask. If you do that, there will be an additional drop added onto your titration flask, and it will give you a measurement that has a significant error in it. So we do not want that to happen. So please make sure that you don't force that droplet into your titration flask. After measuring exactly 25.00 cubic centimeters of our potassium oxalate solution, we have to add 15 cubic centimeters of dilute sulfuric acid. Now, when you are measuring the dilute sulfuric acid, we do not have to use a pipette because we are titrating potassium oxalate. Addition of dilute sulfuric acid is done just to make this solution acidic. We do not need to measure the volume of sulfuric acid that precisely. So we can use a measuring cylinder. We do not have to use a pipette. We will be using a measuring cylinder to measure 15 cubic centimeters of sulfuric acid. Each time whenever you make a measurement, especially using a measuring cylinder or a burette or a pipette, you have to make sure that you bring the meniscus to your eye level to see if you have measured it properly. After you measure exactly 15 cubic centimeters of dilute sulfuric acid, we can transfer it into our potassium oxalate solution over here. And now we will give it a little swirl. We'll swirl the solution around a little bit, and then we have to go on ahead and heat this solution. So in order to do that, we will be using a spirit burner and a tripod and a wire mesh. So we will light the spirit burner first. After lighting the spirit burner, we can place our tripod and a wire mesh like this. So it is important to make sure that we place a wire mesh because it will help in distributing the heat evenly and making sure that the heat that is provided by the spirit burner is received by the beaker, or in this case a titration flask, evenly. So we will place the titration flask over here and allow it to warm up for a few minutes. And then now we will be moving on to filling up our burette with the potassium permanganate solution. All right. Students, now we have washed this burette with distilled water and the potassium permanganate solution, and we have filled it up to the zero line in the burette. So now we can move on to our titration. As you can see, we started off with heating our solution in our titration flask. This was done because this reaction we are about to do progresses very slowly at room temperature. So by heating it up, we make sure that the reaction takes place at a faster pace. So now let's start our titration. We are expecting the color of this potassium permanganate solution to remain stable for a while, but as you can see, once you add a little bit of potassium permanganate and when you allow it to react with the solution a little bit, with time it completely disappears. This is because the potassium permanganate reacts with the oxalate anion and converts MnO4 minus into Mn2 plus. MnO4 minus is a dark purple color with a high color intensity, but when you turn MnO4 minus ions into Mn2 plus, the color of Mn2 plus is a almost colorless color. So basically, we looked at in the previous practicals, we looked at the colors of Mn2 plus aqueous solutions. It is supposed to be a very slight pink color. However, we do not necessarily observe that color in lower concentrations of Mn2 plus. So what we are seeing here is a disappearance of this dark purple color when MnO4 minus ions convert into Mn2 plus ions. When this is happening, since MnO4 minus is a good oxidizing agent, it oxidizes the oxalate anion and converts the oxalate anion into carbon dioxide. As you can see, when we add potassium permanganate, the color of the potassium permanganate disappears completely. We need to do this titration while heating the solution constantly. So if the solution cools down significantly, we will again place it on our heating mantle over here, and we will heat it a little bit to make sure that we carry this titration out at a higher temperature than room temperature. When we are doing a titration like this, we can see when we add a little bit of potassium permanganate, how long it takes for the color of the potassium permanganate to disappear. If the color of the potassium permanganate disappears quite fast, that means we are not very close to the end point. If it takes a little while longer, that means we are nearing the end point. But when it comes to this particular titration, it could mean the temperature of the solution also is not enough. At that point, we can try to heat it up again and see if the color disappearance takes place at a faster rate. The solution seems to be cooled down a little bit. So let us heat it up a little bit more. Again, the reason why we are heating up this solution is because this reaction between potassium permanganate and the potassium oxalate in acidic medium happens at a slower rate at room temperature. So we need to make sure that we increase the temperature a little bit for this reaction to happen at a faster rate. So that is why we have placed this again on our spirit burner to make sure that we increase the temperature a little bit more so that the reaction can happen faster, so that we can see a clear endpoint at the end of this titration. Now, let's continue on with the titration. Students, now you can see that we are observing a permanent pink color. Now this color is permanently there due to all of the oxalate anions reacting with the potassium permanganate that we added into this solution. So after all of the oxalate anions are completely reacted, the next oncoming drop of potassium permanganate will make the entire solution a slight pink or slight purple color. So at this point, we can see that we have successfully obtained our endpoint. So after obtaining our endpoint, we need to observe the reading of the burette. So let's go on and take a reading or take a look at the reading of our burette. So our burette reading is at 31.6. So our first burette reading is at 31.6. Just like this titration, we have to do 2 more titrations so that we have enough and more measurements to move on to a calculation, knowing that we did not make a lot of mistakes. So whenever we have 3 measurements, we can be sure that these measurements or the method that we followed was correct, and if the 3 measurements are closely related to each other, we can argue that the measurements are concordant or they are precise, so that we can move on to calculate the concentration of the potassium permanganate in this burette. So let's move on and try to do 2 more titrations against potassium permanganate solution. Students, now we will be doing our second titration. So just like in the previous titration, we have prepared a solution to our titration flask. In order to make this solution, we took 25 cubic centimeters measured with a pipette of potassium oxalate solution, and then to that we included 15 cubic centimeters of dilute sulfuric acid. And as you can see here, we have filled our burette again up to the 0 point, so that when we are doing our titration, we will have enough and more potassium permanganate to carry out our titration. So let's move on to our second titration. Just like in the previous titration, we have heated up our solution, and if we need to heat it up in the middle, we will go ahead and do so. For the time being, it is at a temperature of around 60 to 70 degrees Celsius. So now let's start our titration. Now, you might have noticed that I started adding potassium permanganate rather rapidly. The reason for that is because now, since we have done our first titration, we have an idea where our endpoint would lie. Our endpoint for the first titration was obtained at 31.6 cubic centimeters of burette reading over here. So up until that point, without any hesitation, we can add our potassium permanganate solution onto our titration flask. So let's say till about 25 cubic centimeters, you can add our potassium permanganate rather rapidly. From that point onwards, you can take it slow and add potassium permanganate into this titration flask little by little. So let's go ahead and do that. Students, now I have added about 27 cubic centimeters of potassium permanganate into this titration flask. From this point onwards, I will be adding potassium permanganate little by little into our titration flask. Students, now you can see that the color of this solution is having a permanent pink color. So this permanent pink color again is due to reaching the end point of this titration. Now all that is left for us to do is take the burette reading over here. So if you take a look at the burette reading now, it is exactly at the same reading as before. It is exactly at the same reading as before, 31.6. So the reading of the second titration was also exactly 31.6. This is a good indication, kind of giving us an idea that the titration reading has been precise. That means we have been following the right methods. Our measurements have been somewhat accurate. So let's move on to our third titration and see if we can get similar results for the third titration as well. We have completed 2 titrations. Now let's move on to the third one. So just like in the previous 2 titrations, to a titration flask, we have added 25.00 cubic centimeters of our potassium oxalate solution. We have added 15 cubic centimeters of dilute sulfuric acid, and then we have placed it on a spade burner and we have heated it up to about 60 to 70 degrees Celsius. And apart from that, we have refilled our burette with our potassium permanganate solution that is going to be used for the titration. So with all of this in place now, we can start our third titration. In this titration, just like the second titration, since we know end point is going to be somewhere near 31.6, we can start adding potassium permanganate rather rapidly to about 25 cubic centimeters, and then from that point onwards we will slow down and we will add potassium permanganate little by little to obtain our endpoint more clearly. Students, now I have added about 26 cubic centimeters of potassium permanganate into this solution. Let's start adding potassium permanganate little by little. We are now at 30 cubic centimeters. So you can start adding potassium permanganate drop by drop to clearly identify the end point of this titration. Now we have obtained our endpoint over here. The endpoint over here is signified by a permanent pink color or a permanent slight purple hue that you observe over here in the titration flask, just like in the previous two titrations. So this is an indication that we have obtained our endpoint. All that is left for us to do is taking a look at the burette reading at this point. So the burette reading at this point is exactly 31.5. So the burette reading is 31.5. We are not at 31.6, but 31.5 is still a concordant burette reading, because the previous two burette readings were 31.6. Both first and the second titration was 31.6, and the third one was 31.5, which is quite precise set of burette readings that we have obtained. So with this information now, we can go on ahead and calculate the concentration of this potassium permanganate solution that we have used to carry out this titration. So let's move on to our next session, where we will be discussing how to carry out that calculation as well as some important details about this practical.
Now students, we have learnt about the theory parts that are associated with experiment number 20. Then we moved into the lab, conducted the experiment, and here we are trying to discuss some questions that are associated with experiment number 20, theory knowledge. So the first question, let's take a look at the first question. An iron nail with a rusted surface of total mass 0.30 grams was completely dissolved in 50 cubic centimeters of 0.2 moles per decimeter cube sulfuric acid and 50 cubic centimeters of 0.02 moles per decimeter cube potassium permanganate was required for complete reaction with the solution thus obtained. Rust can be assumed to be entirely ferric oxide. Ferric oxide means Fe2O3. We can assume that rust is mainly or completely, not mainly, completely Fe2O3. And then we have three questions given here. Write the balanced equations for what happens with ferric Fe2O3, ferric oxide with, and then we have to write equations, balanced equations for the dissolution of rusted iron nail in sulfuric acid. Write balanced chemical equation for the reaction between Fe2 plus and potassium permanganate in acidic medium, and calculate the mass of iron nail before the corrosion, and the relative atomic masses are given here. So students, in this particular question that they are asking us, we have to understand that there is a nail that has a total mass, of 3 or 0.3 grams. The total mass of the nail is 0.3 grams. But on top of the nail, there is rust. So this is rust. Basically, Fe2O3, ferric oxide. Ferric oxide. And what you have over here in this region is our Fe solid that is not yet rusted. And the overall mass of this, both rust and Fe, so I can write that down over here, both Fe solid as well as Fe2O3 solid on the nail, overall mass of this nail is going to be 0.30 grams. That's what the question says. We need to first understand what the question is telling us. So after understanding this part very clearly, we can now move on to answering the first question. Write the balanced chemical equation for the dissolution of a rusted iron nail. So students, iron, Fe, can react with sulfuric acid and produce FeSO4, ferrous sulfate. Right, so Fe can turn into FeSO4 and H2. So this is going to be aqueous. This is also aqueous. This was solid. So now we can balance it off. We can see 1 ferrous, 1 ferrous, 1 sulfate, 1 sulfate, 2 hydrogens, 2 hydrogens. Equation is balanced. This is going to be your first reaction. Now we are going to take a look at what happens when ferric oxide, Fe2O3, solid, is reacted with sulfuric acid. So when this reaction takes place, students, we can see this ferric ions here will form ferric sulfate by joining with sulfate ions. So the formula is going to be Fe2SO4 3 times, because there will be 3 sulfate ions that are joined with 2 ferric ions, and then 3 water molecules will also be produced over here, students. And to balance it off, we'll have to add 3 over here, and the number of ferric ions and number of sulfate ions as well as hydrogens are going to be all balanced, and water, oxygen in water is going to be balanced here by oxygen seen in ferric oxide. So these are the main 2 reactions, balanced reactions that you can write as the answer for the first question. And then we can move on to the second question. Write the balanced chemical equation for the reaction between Fe2 plus and permanganate ions. Now students, we already know what is happening here. Ferrous in the medium can undergo oxidation in the presence of acidified potassium permanganate and turn into ferric, releasing an electron. So this is going to be your reaction number 1, which is our oxidation reaction. This is a oxidation that is taking place. And permanganate ions in the medium. Now, how do we know this is acidic? Because we dissolve the iron nail in sulfuric acid. So this medium is acidic. And we have permanganate added to this. So permanganate in acidic medium can act as an oxidizing agent and oxidize Fe2 plus into Fe3 plus. So when that happens, we can write KMnO4. Now you should be quite proficient at writing this because we have written permanganate reaction, half equation for permanganate undergoing reduction so many times. So in acidic medium, permanganate turns into manganese 2 plus or Mn2 plus. And at this point, you will observe the number of oxygens are not balanced on both sides. So we will have to add water to balance that off here. There has to be 4 water to balance the number of oxygens on the left hand side. And when you do that, number of hydrogens are not balanced, 8 H pluses. And when that happens, you will see both sides atoms are balanced but not charges. And to balance charges on both sides, after seeing that this has altogether plus 7 charge and over here only plus 2 charge, to bring down the plus 7 charge to a plus 2 charge, we can add 5 electrons. So then the overall charge on the left hand side is plus 2 and the right hand side is also plus 2. So this is going to be our reaction 2. And the number of electrons taken in by the reaction 2 is not equal to the number of electrons given out by reaction 1. So to balance that, we can multiply reaction number 1 by 5 and then add that to reaction number 2, because when you multiply reaction number 1 by 5, number of electrons released will be 5, and in the reaction 2, number of electrons taken in will be 5. So electron number will be balanced. So then we can write the final balanced ionic equation this way: 5 Fe2 plus 8 H plus KMnO4 minus turns into 5 Fe 3 plus Mn2 plus and 4 H2O. So this is going to be our balanced ionic equation, students. So we have now what one of the reasons why it is very important for us to write this is to observe the reaction ratio. The only thing that is present in the medium that can get oxidized is ferrous. Other than that, we have ferric as well, but ferric is not going to be oxidized further. So only thing that can be oxidized by acidified potassium permanganate is ferrous. So when you observe this, you get to observe the permanganate ion 2 Fe2 plus, permanganate ion 2 Fe2 plus reaction ratio, and that is going to be 1:5. 1:5. With 1 permanganate, 5 Fe2 plus will react. So after noticing that, we can now move on to the next part. Calculate the mass of iron nail before corrosion. Calculate the mass of iron nail before corrosion. We observed that there is a certain amount of moles of Fe solid. Right? There is a certain number of moles of Fe solid. And We have ferric oxide as well, and mass of both of these in the nail was 0.30 grams. So when you combine the masses of both of them together, the overall mass was 0.30 grams. Now in the previous observation that we made over here, the permanganate ions, now in the question they're asking us only to write the balanced chemical equation between permanganate and Fe2 plus. So you can see we have now developed this equation and we know the reaction ratio between permanganate and Fe2 plus. And in the question they have given us the number of moles of permanganate that was spent on reacting with Fe2 plus that was available in the medium, right? They have mentioned after completely dissolving 50 cubic centimeters of acid, we had to spend 25 cubic centimeters of 0.02 moles per decimeters cube concentrated potassium permanganate to completely react with the Fe2 plus present in the medium, because the only thing that can react with potassium permanganate at this point is Fe2 plus. So permanganate ion concentration is given and the volume that needed to react with all of the Fe2 plus in the medium is given. Then at that point we can find out the number of moles of Fe solid that was present there. So they say when we were carrying out a titration, 0.02 m KMnO4 was used to titrate this solution. In this solution, only substance that could undergo oxidation was Fe2 plus. And we have ended up spending 25 cubic centimeters. We have ended up spending 25 cubic centimeters of potassium permanganate to react with the remaining amount of Fe2 plus in the aqueous medium. Always double check your details. 25 cubic centimeters of 0.02 moles per decimeters cube of potassium permanganate was required for complete reaction with the solution obtained. So in the solution obtained, only thing that could react with potassium permanganate was Fe2 plus. So that means using these details, students, we can calculate the number of moles of potassium permanganate. So if you carry out a calculation for potassium permanganate, we can calculate the number of moles using concentration multiplied by volume. Concentration is 0.02 moles per decimeters cube. And volume is going to be 25 cubic centimeters. So you can divide this by 1000 to convert into cubic decimeters. So you can see per decimeters and decimeters cancel off and you will get to the final answer 0.5 divided by 1000 moles. So this is going to be the number of moles of potassium permanganate, 0.5 divided by 1000, or else if you want you can keep it in the exponential form, which is 5.0 into 10 to the power minus 4 moles. This is also correct. So this is the number of moles of potassium permanganate. So in the previous slide we observed potassium permanganate to Fe2 plus ratio is 1:5. So we can copy that down over here. We know this permanganate to Fe2 plus. Ratio is 1:5. And we have already found out permanganate number of moles. Permanganate number of moles is 5 into 10 to the power minus 4 millimoles. So if that is the case, students, can you find out the Fe2 plus number of moles? Yes. This many moles multiplied by 5. So that's going to be 25 into 10 to the power minus 4. But we can just write it as 2.5 into 10 to the power minus 3 moles. So keep in mind the 10 to the power figure I have changed. Otherwise, you can just write 25 into 10 to the power minus 4. That is also acceptable. So this is the number of moles of Fe2 plus present in the medium. So if you know the number of moles of Fe2 plus, then we can find out the number of moles of iron solid that was present in the iron nail. So we know that Fe solid is what got converted into Fe2 plus. So if you have X amount of moles here, then X amount of moles would be present here in the iron nail as well. So if you know this, since we know Fe solid to Fe2 plus ratio is 1:1, we can conclude that Fe solid amount in the nail is equal to 2.5 into 10 to the power minus 3 moles. And we know Fe molar mass. Fe molar mass is going to be 56 grams per mole, right? Molar mass of Fe. Molar mass of Fe is going to be 56 grams per mole. So at that point, we can calculate mass of Fe solid in the rusted nail. Only the Fe solid in the rusted nail is going to be equal to number of moles 2.5 into 10 to the power, it should be 2.5, very clearly written, 2.5 into 10 to the power minus 3 millimoles multiplied by molar mass, which is 56 grams per mole. So per mole, mole cancels off, and we can then write the answer in moles is 140 into 10 to the power minus 3 grams. So when you multiply these two, it is going to be 140 into 10 to the power minus 3 grams. So that means 0.140 grams, 0.140 or 0.14 grams. So in the iron nail, we had a iron nail like this. 0.14 grams was iron solid, basically Fe solid. And then on it, there was rust, right? Rust was Fe2O3. And the overall mass of the entire nail with rust was 0.3. So we can write an equation Fe2O3 solid mass is equal to overall mass of rusted nail minus mass of iron solid. So the total mass of the iron nail was 0.30 grams minus mass of just the iron solid was 0.14 grams. So that would indicate that the number of grams of Fe2O3 ferric oxide is going to be 0.16 grams. So this is going to be our number of grams of ferric oxide. So the question asks, what is the mass of the iron nail before rusting occurred? That means we need to find out the total mass of just the iron in rust. The total mass of just the iron in rust. So when you are considering ferric oxide, we know its mass now, right? So if you know the number of, or if you know this equation, then you know, if you know the mass of a substance and the molar mass of that substance, we can find out the number of moles of the substance. So ferric oxide molar mass is still not known to us. We can calculate that. There are 2 Fe in ferric oxide, so 2 multiplied by 56. Oxygen, there are 3 of them. It should be multiplied by 16. So then we have here 112 plus 18, actually 48, not 18. So when you add them together, it is going to be 160. So students, molar mass of iron oxide or ferric oxide is going to be 160 grams per mole, and the mass of just the ferric oxide is going to be 0.16 grams. Molar mass is 160 grams per mole. So the number of moles of just ferric oxide is going to be 0.16 multiplied by 160. So this is going to be 0.001 moles. Now, each ferric oxide contains how many ferric ions? In each ferric oxide, there are 2 ferric ions. So what got converted into ferric when forming rust was iron. So if you know the number of moles of ferric oxide that is present in the nail, we can find out the number of moles of iron, right? We can write amount of Fe3 plus in 0.16 grams of ferric oxide is going to be 0.01 multiplied by, actually 0.001 multiplied by 2. So this is going to be 0.002 moles. And because of this, we can now calculate the mass of just the iron coming from ferric oxide. We can write mass of Fe solid that comes from Fe2O3. So what we are trying to do is we are trying to figure out how much of iron is found in ferric. So mass of just the iron in ferric oxide is going to be 0.002 moles multiplied by the molar mass of Fe, which is 56 grams per mole. Moles and per moles cancel off, and it's going to be 0.112 grams. 0.112 grams. So this is the mass of iron that comes into the iron nail if you convert the amount of iron in ferric oxide. So we already know the mass of iron that did not get converted into ferric oxide, and now we have found out the mass of iron that was in ferric oxide. So we can write mass of the nail before rusting took place. Before rusting is going to be equal to mass of just the iron nail, which is 0.14 grams. We found that out earlier, and then we found out the mass of iron that actually got rusted. So, and that iron had a mass of 0.112 grams. So the final answer is going to be 0.252 grams. So this is the mass of the iron nail before it got rusted. So we can double check whether this answer is correct by thinking back on what was the mass of the nail after rusting has taken place. So the nail's mass before rusting should not be greater than the nail's mass after rusting, because when rusting takes place, oxygen also comes into the iron nail. So that means mass of the nail increases when rusting has taken place. So over here, we have not surpassed 0.3 grams. Actually, this is 0.252 grams, which is smaller than 0.3. That means we have calculated this particular mass accurately. So students, this is how you will approach a question like this one. Let's move on to the next one. Now let's take a look at the second question. Solution B contains oxalate and carbonate ions, 25 cubic centimeter portions. 25 cubic centimeter portions of this solution was treated with excess calcium nitrate solution to completely, it's very important, completely precipitate oxalate ions and carbonate ions, and the mass of the resulting precipitate after drying it was 0.820 grams. This precipitate was then dissolved in dilute sulfuric acid and titrated with 0.05 moles per decimeter cube concentrated potassium permanganate solution. And 20 cubic centimeters of that KMnO4 solution was required for the titration. They're asking us to calculate the concentrations of oxalate and carbonate in solution B. So let's try to understand what is the question here. So that is solution B. This is solution B. This contains both oxalate ions and carbonate ions. And we are going to take just 25 cubic centimeters of it Here we only have 25 cubic centimeters. And we are adding excess calcium nitrate to this. So in the presence of calcium 2+ ions, oxalate and carbonate will precipitate, students. So oxalate and carbonate will precipitate as calcium carbonate. Actually, if we talk about oxalate ions first, calcium oxalate will be precipitated out, as well as calcium carbonate. So these are the precipitates that are seen here. And then we are going to take this precipitate out and we are going to dry it and weigh it. So still we have here calcium oxalate. Now it is a dried solid, as well as calcium carbonate. And the mass of both of these solids together, in this question it says 0.820 grams. 0.820 grams. So this is what this question tells us. And then we take that dried solid, dissolve it in sulfuric acid, or we can directly do it in a titration flask as well. So we will add the solid, and then we will add enough and more sulfuric acid to it. So when sulfuric acid is added, students, both calcium carbonate and calcium oxalate will dissolve, but calcium carbonate contains carbonate ions. Now carbonate ions, when reacted with an acid, it will produce carbonic acid, CO3. And carbonic acid can undergo decomposition, because carbonic acid is not a very stable acid. Actually, immediately it breaks down to form water and carbon dioxide gas. So carbon dioxide gas will leave the system. So once you take the solid that you see over here and dissolve it in sulfuric acid, the main substance that you have over here is just oxalate ions. The carbonate ions are going to leave the system as carbon dioxide. So you only have this oxalate ions. And then we are going to titrate this with the use of 0.05 m KMnO4. And in the question it says, students, that 0.05 moles per decimeters cube potassium permanganate was used, and 20 cubic centimeters of this solution was required for the titration. So what is the volume of this solution that was required? 20 cubic centimeters. So now we have noted down all of the information that is related to this particular question. So whatever the number of moles of oxalate that we have over here originally came all the way from just 25 cubic centimeters of solution B. We took 25 cubic centimeters of solution B, right? So whatever the number of moles of oxalate that we find out from this titration came from this 25 milliliters of solution B. And if you know the number of moles of oxalate through this titration, if you can find it out, then we can find out the calcium oxalate mass that is seen in this precipitate. So if you know the calcium oxalate mass, then we can find out the calcium carbonate, because we know the total mass. If you know the calcium oxalate, since you know the total mass, you can find out the calcium carbonate mass. So when you know their masses, we can find out their concentrations as well. So that is how we are going to approach this question. Now, first of all, we can proceed to write down the equations pertaining to this question. Now, first thing that is taking place here is calcium 2 plus aqueous ions will react with oxalate aqueous ions to form calcium oxalate solid. That's reaction number 1. And then we have calcium 2 plus aqueous reacting with carbonate ions in the medium, turning into calcium carbonate solid. And then once you react calcium carbonate and calcium oxalate with sulfuric acid, again another set of reactions can be observed. So when you take calcium oxalate solid and reacted with sulfuric, we can observe the formation of calcium sulfate and oxalic acid. Calcium sulfate and oxalic acid. And then when you react calcium carbonate with sulfuric, we will form again calcium sulfate with water and carbon dioxide gas. Calcium sulfate, water and carbon dioxide will be formed. So these are the main reactions that are taking place before the titration is carried out. Then we will be carrying out a titration. So in that titration, we remember when oxalate anion is titrated with acidified potassium permanganate, we saw carbon dioxide was produced, releasing 2 electrons. So this is reaction number 1, oxidation. When potassium permanganate or MnO4 minus was reacted in acidic medium. So this medium is acidic because we are dissolving the precipitate in sulfuric acid. So this medium is acidic. So when you're adding potassium permanganate, it is reacting in acidic medium, so it turns into Mn2 plus 4H2O 8H plus. Now you have balanced this equation so many times. I'm quite sure that all of you are familiar with how to balance an equation like this. In the theory parts of this practical, we discussed this equation and how to balance it. And that is reaction number 1, reaction number 2. So number of electrons given out in reaction number 1 and number of electrons taken in by reaction number 2 are not the same. So if you multiply reaction number 1 by 5 and then add to reaction number 2 multiplied by reaction number 2 multiplied by 2, we can see the number of electrons will balance off. When you multiply this entire reaction by 5, electron number will be 10. And when you multiply this entire second reaction by 2, the number of electrons here will also be 10. So at that point, we can write over here, we can start with this. We can write 16 H pluses and 2 permanganate, 5 oxalate, will turn into 10 carbon dioxide. Two Mn2 plus, 2 Mn2 plus, and 8 water. So when this happens, we have now written down the balanced ionic equation. So this is quite important for us because we are in the process of finding out the number of moles of oxalate ions that were present in the medium. And in order to do that, we need to find out the reaction ratio between permanganate and oxalate. Why? Because we carried out a titration between permanganate and oxalate. So you can see here KMnO4 2 minus 2, or permanganate, actually not 2 minus, KMnO4 minus permanganate to oxalate C2O4 2 minus, ratio is 2:5. With every 2 permanganate ions, 5 oxalate ions will react. So note it down. And then we know there was a titration that was carried out. In this titration, we use potassium permanganate, KMnO4, and we can calculate the number of moles of potassium permanganate that was used to titrate the oxalate ions present in the medium with the use of its concentration and the volume. We know concentration was 0.05 moles per decimeter cube and volume was 20 cubic centimeters. So concentration is 0.05 moles per decimeter cube and the volume was 20 cubic centimeters. So we can divide this by 1000 to convert it into decimeters cube. Immediately you can see decimeters cube and per decimeters cube cancel off. And then we have 20 multiplied by 5 is 100. Now there are 2 decimal places here. That means 1 divided by 1000 is going to be our answer when you solve this. So 1 divided by 1000 moles. You can keep the answer in this form as well. 1.0 into 10 to the power minus 3 moles. Right, students. So now we have found out the number of moles of KMnO4. And we know the reaction ratio between the two. So actually, if you know the number of moles of KMnO4, which is going to be 1.0 into 10 to the power minus 3 moles, if you know the potassium permanganate moles, then can you find out the oxalate number of moles? Yes. You'll have to divide this number by 2 and multiply it by 5. So we can write 1.0 into 10 to the power minus 3. This number has to be divided by 2, multiplied by 5. Divide by 2, multiplied by 5. So we can write down that answer here. So you can write amount of C2O4 found in 25 cubic centimeters of solution B, because all of these oxalate ion number of moles that you find here originally came from just the 25 milliliter portion of solution B we took for this experiment. So that can be written as 1.0 into 10 to the power minus 3 multiplied by 5 divided by 2. This many moles. Or in other words, 2.5 into 10 to the power minus 3 moles. So this many moles of oxalate anion is found in 25 cubic centimeters of our solution B. So then we can calculate, because of this, we can calculate concentration of oxalate C2O4 2 minus in solution B. It is going to be equal to this number of moles divided by volume. 2.5 into 10 to the power minus 3 moles should be divided by the volume. Now I told you all of these number of moles were present in 25 cubic centimeters of solution B. So this has to be divided by the volume of solution B, which is 25 that we have taken. To convert 25 into decimeters cube, we will have to multiply it with 10 to the power minus 3, or we can divide by 1000. So this is going to be now decimeters cube. You can see 10 to the minus 3, 10 to the minus 3 cancels off, and the answer is going to be 0.1 moles per decimeters cube. This will be our answer, students. This is going to be our answer. So this is the answer to the first part, the concentration of oxalate ions in solution B. So once you find this, then we can use the number of moles of oxalate ions present in the medium now to calculate the mass of calcium oxalate. And then with that we can proceed to finding the concentration of calcium carbonate as well. So now let's move on to that. We'll start that in a separate area. So we know the number of moles of calcium, or we know the number of moles of oxalate ions. Number of moles of oxalate ions is going to be, or we can write amount of oxalate in the medium is equal to 2.5 into 10 to the power 2.5 into 10 to the power minus 3 millimoles. So we found this out in the previous calculation. So if you take a look at the equation that we wrote earlier, calcium 2 plus and oxalate C2O4 2 minus will form calcium oxalate, which is a solid. So the reaction ratio is 1:1. So that means if you know the calcium, or if you know the oxalate number of moles, then you know the calcium oxalate number of moles as well, because their ratio is 1:1. Since we have already found out the oxalate number of moles in this medium, which happens to be 2.5 into 10 to the power 5 minus 3 moles, we would find out the number of moles of calcium oxalate, which is going to be the same, 2.5 into 10 to the power minus 3 mole. So we now know the number of moles of calcium oxalate that is present in the medium, actually in this case that is present in the precipitate. So can we find out its mass? Yes, we can. So let's say calcium oxalate mass is equal to number of moles multiplied by molar mass. Number of moles multiplied by molar mass. We derived that from this equation, N is equal to simple M divided by capital M. But now we have to find out calcium oxalate's molar mass. Now calcium has a mass of 40. Carbon, there are 2 carbons, each carbon is 12. 12 into 2 is 24. There are oxygens, each oxygen is 16. 16 into 4, there are 4 oxygens. So 16 into 4 is 64. So when you add them all together, you can see 8 here and 12. 128 will be the calcium oxalate's molar mass. 128 grams per mole. So we have 2.5 into 10 to the power minus 3 moles multiplied by 128 grams per mole. So when you solve this, it's going to be 320 multiplied by 10 to the power minus 3 grams, because you can see moles and per moles cancel off, the answer will come in grams. So 320 into 10 to the power minus 3 means 0.32 grams. 0.32 grams. So this is the mass of just calcium oxalate in the precipitate. Now, can you remember, students, we learned that both calcium carbonate solid, or the mass of the calcium carbonate precipitate added with calcium oxalate solid was equal to 0.82 grams. So if that is the case, if you know the calcium oxalate precipitate mass, then we can find out the calcium carbonate precipitate mass. So we can write down, because of these findings, mass of calcium carbonate in the precipitate is equal to 0.82 grams minus 0.32 grams. So the answer is going to be 0.50 grams. So this is the mass of calcium carbonate. This is the mass of calcium carbonate precipitate. So students, now it is time for us to find out the concentration of carbonate ions. So if you know the mass of calcium carbonate, with the use of this equation, number of moles is equal to molar mass of substance divided by molar mass. With the use of this equation, we can find out the number of moles of calcium carbonate. So students, calcium carbonate is something that you should remember the molar mass of. It's very easy, it's 100. But we'll calculate it here just for your reference. Calcium has a mass of 40. Carbon has a mass of 12. And oxygen. Each oxygen is 16, but there are 3 of them, so therefore it is 48. 48 plus 12 is 60. 60 plus 40 is 100. So when you're talking about calcium carbonate, we can find out the amount of calcium carbonate, amount or number of moles of calcium carbonate is equal to, over here we know the mass, which is 0.5 grams, and we just found out the molar mass, that is 100 grams per mole. That is 100 grams per mole. So at that point we can see both gram, our signs here cancels off. So the answer is going to be 0.005 moles. This many moles are going to be seen here. This many moles are going to be seen in the calcium carbonate part of the precipitate. Now, after finding the number of moles of calcium carbonate, we can revisit the equation here. Calcium carbonate was formed when calcium 2 plus reacted with carbonate ions to form calcium carbonate solid. So you can see the reaction ratio between carbonate and calcium carbonate is 1:1. So we can write carbonate ions to calcium carbonate ratio is 1:1. So if you know that, and if you happen to know the number of moles of calcium carbonate, which is 0.005, then you can easily find out the number of moles of carbonate ions. That is also going to be 0.005 because the reaction ratio is 1:1. So when you do this, since you have already found out the number of moles of calcium carbonate, we can directly write this statement here. Just to be clear, we can write amount of carbonate ions in 25 cubic centimeters of solution B. And that is going to be 0.005. We have just found it out, this many moles. Then we can write, therefore, concentration of carbonate in solution B, which happens to be 0.005 moles divided by the volume, in this case 25 cubic centimeters. We can convert it into decimeters cubed by multiplying it with 10 to the power minus 3. And when you do that, you get to this answer, 5 divided by 25, which is 1/5. As you know, 1/5 is just 0.2 moles per decimeters cube. So this is the concentration of carbonate ions in the medium, 0.2 moles per decimeters cube. And concentration of oxalate ions in the medium was 0.1 moles per decimeters cube. So we have now answered the question that was asked of us, which is what is the concentration of carbonate ions and oxalate ions in solution B. So again, this was a question with a few steps. I hope you will be able to approach a question carefully like the way we did and obtain the final answers correctly. So now let's move on to the next question. Now let's take a look at the third question. Y solution contains dilute sulfuric acid and oxalic acid. 25 cubic centimeters of this solution was titrated with 0.05 moles per decimeters cube potassium permanganate solution. The required volume of potassium permanganate solution was 24 cubic centimeters. So if you only have a solution containing sulfuric and oxalic acid, what can undergo oxidation when we are reacting with an oxidizing agent like potassium permanganate? Only oxalic acid. So this medium is already acidic. So potassium permanganate in acidic medium can oxidize oxalic acid into carbon dioxide. And in order to do that, in order for the reaction to completely take place, we have spent 24 cubic centimeters of the potassium permanganate solution. Now, after completing the titration of 1, the resulting solution was further titrated with 0.04 moles per decimeters cube concentrated sodium hydroxide. Now, what can get titrated with sodium hydroxide? There should be an acid. Sodium hydroxide will get titrated with an acid, reacted with an acid. So the volume of sodium hydroxide required was 15 cubic centimeters. So originally in this question they say, initially actually, they say sulfuric acid was there. And when the reaction is taking place, both sulfuric acid and oxalic acid will take part in the oxidation of oxalic into carbon dioxide. So a certain amount of sulfuric will be spent in the first stage of this reaction, and then the remaining amount of sulfuric was reacted with sodium hydroxide. And in order to titrate the remaining amount of sulfuric, we have spent 0.04 moles per decimeter cube concentrated sodium hydroxide, and we have spent 15 milliliters of that solution. And first they ask you to write the balanced chemical equations, and then they're asking us to calculate the concentration of oxalic acid and calculate the concentration of sulfuric acid. In the first part of this question, we have the balanced chemical equations you need to write. So you need to write the balanced chemical equation. So we have oxalic acid, C2O4, 2 minus, actually in this case we are dealing with oxalic acid, so we can write H2C2O4, and it gets oxidized in presence of acidified potassium permanganate to form carbon dioxide. So 2 carbon dioxides will be produced along with 2 H pluses and 2 electrons. This is your first half equation. This is your first half equation. And we can write another half equation for the reduction of permanganate ions. So we see here permanganate ions KMnO4 minus. It reacts with oxalic acid to form Mn2 plus 4H2O, 8 H pluses and 5 electrons here. And this is going to be your reaction 2. Now again, students, you will observe that reaction 1 and reaction 2, the electrons do not balance. But if you multiply reaction 1 by 5 and add to reaction 2, which is also multiplied by 2, then the reaction would be written like this. So the reaction 1 should be multiplied by 5. So at that point we'll have 5H2C2O4, and reaction 2 is multiplied by 2. So you would have altogether 16 H pluses and 2 permanganate ions, MnO4 1 minus. And over here, since you're multiplying the first reaction by 5, we have 10 carbon dioxide and 10 H pluses. And over here we have 2 Mn2 pluses and 8 H2O. Now you can see on both sides we have H pluses. We don't need to have H pluses on both sides. So we can now remove the right number of H pluses from both sides. So 16 H pluses here, 10 H pluses here. So on the left hand side there are a greater number of H pluses. So when you remove 10 H pluses from 16, you are left with just 6 H pluses here. Just 6 H pluses here. So now students, this is going to be your final equation. We have 6 H pluses reacting with 2 MnO4 minus and 5 oxalic acid to turn into carbon dioxide, 10 carbon dioxide, 2 Mn2 plus and 8 water molecules. So you can double check if the number of hydrogens are balancing off. There are 8 hydrogens here, 8 hydrogens there. You can see if the oxygens are also balancing off. There are 20 oxygens and 8 oxygens there, altogether 28 oxygens. Over here there are 20 and MnO4 minus, there are 2 of them bringing in 8 oxygens, so altogether 28 oxygens. That is also balanced. So now we can write down an equation including from where these H pluses are coming from. So H pluses additionally come into this medium with the use of sulfuric acid. So when we have used sulfuric acid to acidify the medium, these H pluses actually come from sulfuric acid. So each sulfuric releases 2 H pluses, so I can write down the equation this way. 3 sulfuric along with 2 potassium permanganate KMnO4 and 5 H2C2O4 turn into 10 carbon dioxide we have 2 Mn2 plus. Now since I wrote potassium permanganate not in the form of permanganate ions, I have to include 2 potassium ions as well. And apart from that, water, H2O, 8H2O will also be present here. So students, this is how you will write the equation. So here the sulfate and ions that are going to be introduced into this particular side of the equation will also be present. You can write them as sulfate, or you can join the sulfate ions and potassium ions together and write potassium sulfate as well. So over here, this is going to be your main equation that you need to look into, because what we are most interested in here is what is happening, or what is the reaction ratio between sulfuric, potassium permanganate and oxalic acid. So you can see when the reaction is taking place, the KMnO4 to oxalic acid ratio is going to be 2:5. This is the ratio, 2:5. And with each potassium permanganate, you can see 3 oxalic acid also, or 3 sulfuric acid also has taken part in this reaction. There is also another observation to make. We can write KMnO4 in this reaction, KMnO4 to sulfuric acid ratio. Sulfuric acid ratio is going to be, for 2 KMnO4, 3 sulfuric acid was used. So we make these observations and then we can move on to the next part. Now let's move on to the part where we find out the concentration of the oxalate ion solution, or ions in the solution, oxalate ions in the solution. And we see when we take a look at this reaction ratio, potassium permanganate to oxalic acid ratio is 2:5. And in this question, they have given us that 0.05 moles per decimeter cube concentrated potassium permanganate was used, and the volume of potassium permanganate used for this titration was 24 cubic centimeters. So we can find out the potassium permanganate number of moles. We can write amount of KMnO4 spent to react with oxalic acid in 25 cubic centimeter solution of solution Y. So that is going to be 0.05 moles per decimeter cube multiplied by 24 decimeters cube. Actually 24 centimeters cube, so we have to multiply this by 10 to the power minus 3 or divide it by 1000. Either method can be used. So decimeters cube and per decimeters cube will cancel off. So the answer can be kept as expression. So we can keep it as 0.05 moles or 0.05 multiplied by 24 divided by 1000, and the unit can be kept as moles because we are talking about the number of moles of potassium permanganate that was found. So 24 cubic centimeters of potassium permanganate was used to titrate this particular oxalate ion content in the solution. So then we have already mentioned that the solution was 25 cubic centimeters. So what we have found out is the potassium permanganate number of moles. So KMnO4 to oxalic acid ratio when they were reacting with one another was 2:5. With 2 potassium permanganate, 5 oxalic acid was reacted. So now we have found out the number of moles of potassium permanganate. 0.05 into 24 divided by 1000 millimoles. So in that case, students, what will be the number of moles of oxalic acid? So since we know the ratio, we have this number of moles. So you can divide this number of moles by 2 and multiply it with 5. So 0.05 into 24, you can divide it by 1000 oh, this is the number of moles that we saw earlier. So this number has to be divided by 2 multiplied by 5. Divide by 2 multiplied by 5. So this is the expression for the number of moles of oxalic acid. So we can write another equation or another statement here. The amount of oxalic acid, or we can just write H2C2O4 in 25 cubic centimeters of solution Y is equal to this 0.05 into 24 divided by 1000 multiplied by 5 divided by 2. Now this is going to, the number of moles comes in moles. So when you solve this, the answer is going to be 0.003 moles. This is going to be the answer for this question, or else you may also keep it as 3.0 into 10 to the power minus 3 moles. Both forms are correct. And then afterwards, so since we have now found out the number of oxalic acid in the medium, we can find out the concentration of, concentration of oxalic acid C2O4, H2C2O4 in solution Y. Concentration, we found out this number of moles was present only in 25 cubic centimeters of solution Y. So then if you take the number of moles and divide it by the volume, which is 25 cubic centimeters. So when you convert 25 cubic centimeters into decimeters cube, you can multiply it with 10 to the power minus 3. So then you have this answer obtained. 3 divided by 25, this many moles per decimeters cube. So if you want to easily solve this, you can multiply both of this numerator and the denominator by 4. So then you will get to 12 divided by 100, which means 0.12 moles per decimeters cube. This is going to be the concentration. 0.12 moles per decimeters cube is going to be the concentration, oxalic acid concentration of solution Y. Oxalic acid concentration of solution Y is going to be 0.12 moles per decimeters cube. So students, we have now found out the oxalic acid concentration. We can now move out to find out the concentration of sulfuric acid. So let's go ahead and find the concentration of sulfuric acid. Now students, we are focusing on sulfuric acid. Now sulfuric acid is going to react with sodium hydroxide that is added to the medium, and we can find out the number of moles of sodium hydroxide that was spent for the titration, and based on that we can find out the number of moles of sulfuric acid that was remaining in the medium. However, if you take a look at the question that we have been given here, we can very clearly see even in the first stage of this reaction, we are using certain number of moles of sulfuric acid. You can see this is the first stage. So when potassium permanganate oxidizes oxalic acid, for each 2 potassium permanganates, 3 sulfuric acid was used. So we saw this reaction ratio. right? So then later on, we have actually moved on to finding the number of moles of potassium permanganate. So we have already found out the number of moles of potassium permanganate here. Amount of KMnO4 was found here. So if you know the number of moles of potassium permanganate, then we can actually find out the sulfuric acid number of moles as well. So we will copy this reaction ratio into the page over here. So sulfuric acid, first of all, is going to be found in two main ways. One, there is a certain amount of sulfuric acid used in the oxidation of H2C2O4, and then remaining sulfuric acid was titrated with sodium hydroxide. So both of these things have taken place. So students, when you're talking about oxidation, we saw KMnO4 to sulfuric acid ratio was 2:3. 2:3. And we have found out the number of moles of potassium permanganate that we have used in this reaction. So we can see 0.05 into 24 divided by 1000. This can actually further be solved to 1.2 divided by 1000. This is the number of moles of potassium permanganate that is used. We can rewrite this if you wish to 1.2 into 10 to the power minus 3 moles. All of these are correct. So that is the number of moles of potassium permanganate, the amount of potassium permanganate that was reacted with oxalic acid. So if you know the amount of potassium permanganate that was in the medium, 1.2 into 10 to the power minus 3 moles, then you can easily find out the number of moles of sulfuric acid that reacted along with potassium permanganate. So we have 1.2 into 10 to the power minus 3. So you have to divide this number by 2 multiplied by 3. Division by 2, multiplication by 3. So then you can write over here a small statement: amount of sulfuric acid reacted with KMnO4 and oxalic acid, but we'll write it as KMnO4. It's going to be, over here we can see they cancel off. It's going to be 0.6. 0.6 into 3 is going to be 1.8 into 10 to the power minus 3 moles. This many moles of sulfuric acid was reacted when the first stage of this reaction was carried out. And in the second stage, now we will note it down and we'll move on to the second stage. In the second stage, we reacted the remaining amount of sulfuric acid with sodium hydroxide. Actually, each sulfuric acid would require 2 sodium hydroxide, so we will be forming sodium sulfate and 2 water molecules. So you can very clearly see the reaction ratio between sulfuric acid and sodium hydroxide is 1:2, 2. Is 1:2. And we can use the concentration of sodium hydroxide and the volume of sodium hydroxide that was spent on this titration to find the number of moles of sodium hydroxide. So students, over here we have the question. We have been given 0.04 moles per decimeter cube concentrated sodium hydroxide and 15 cubic centimeters of it was used. So the concentration was 0.04 and 15 cubic centimeters was used. So we can write NaOH amount used is equal to concentration, which is 0.04 moles per decimeter cube multiplied by 15 cubic centimeters. We can convert it into decimeters cube and write decimeters cube and per decimeters cube cancel off. And we can keep as an expression here. That's going to be 0.04 into 15 into 10 to the power minus 3 moles. It's going to be 0.6 into 10 to the power minus 3 moles. We can leave it as 6.0 into 10 to the power minus 4 moles. So this is the number of moles of sodium hydroxide that was used in this titration. So since we know the sodium hydroxide to sulfuric acid ratio, if we have spent specific amount of sodium hydroxide, half of that is the number of moles of sulfuric acid that was present in the medium. So half of this number is the number of moles of sulfuric acid that was present in the medium. So we can write, because of this, sulfuric acid remaining in the medium is going to be equal to half this number. So 6.0 into 10 to the power minus 4 moles should be divided by 2, which is going to be 3.0 into 10 to the power minus 4 moles. So this is the number of moles that is of sulfuric acid that is remaining in the medium. Earlier on, we found out the number of sulfuric acid moles that reacted with the potassium permanganate and oxalic acid. So it is 1.8 into 10 to the power minus 3. And over here, we have found out the number of moles of sulfuric acid still remaining in the medium. So we can write the total sulfuric acid that was present in the medium (25 cubic centimeters of the medium) this is going to be equal to, we have we'll double check the answer, 1.8 into 10 to the power minus 3 moles, 1.8 into 10 to the power minus 3 moles. We can write this answer as well in 10 to the power minus 3, so we can write it like this, 0.3 into 10 to the power minus 3 moles. Now all of these are in moles. So at that point, when you add them together, the answer would be 2.1 into 10 to the power minus 3 moles. So this is the number of moles of sulfuric acid that was present in 25 cubic centimeters of solution Y. So then we can find out, because of this, we can find out the concentration of sulfuric acid that was initially seen in solution Y. Concentration of sulfuric acid initially seen in solution Y is going to be 2.1. So the number of moles should be divided by the volume of the solution. So we have over here itself mentioned, we have taken 25 cubic centimeters of this solution. So therefore, we are dealing with 25 cubic centimeters. Right, so 25 into 10 to the power minus 3 will convert it into decimeters cube. So you can see 10 to the power minus 3, 10 to the power minus 3 over here cancels off. So then we are left with 2.1 divided by 25. Again, when it comes to a part like this, to solve it faster, you can multiply both the numerator and the denominator by 4. So when you do that, this becomes 8.4 and this becomes 100. So which is going to give us the final answer as 0.084 moles per decimeters cube. This is going to be the concentration, or the final concentration, of sulfuric acid that was present in the medium. So this is going to be the solution Y's sulfuric acid concentration. So we have followed the steps to find out the initial concentration. Actually, this is the initial concentration that we see in solution Y. So sulfuric acid initial concentration in solution Y is going to be this. Right, students, so with that, we have concluded the third question. So we have discussed a few questions here, all revolving around oxalic acid or oxalate ions and oxidation involving potassium permanganate. So by now, students, you should be very familiar with oxidation reactions revolving around the oxidizing agent potassium permanganate and oxidation of oxalic acid or oxalate anion. So we have taken a look at a couple of different questions, and in each of them we saw how to navigate through multi-steps or different steps of different questions. So by now you should have a good understanding of how to approach a question and how to carefully navigate through a question like this and get to the final answer. So with that, students, we can conclude today's experiment, and I will see you again in the next experiment.